So we see we are approaching the end of the lunch break. People are coming again back. Attendees counts become a bit more again. Welcome back after the lunch break to the NanoSafety Cluster Training Day attached to the NanoSafety Digital Conference. Let's have a quick view on the schedule. So we're now going to have a 1 hour, quite intense training session, hands-on, interactive as possible, of the NanoSolvit tools for assessment of human and environmental exposure to nanomaterials by the team of Andreas, who is the coordinator of the project. So at first, Nikos Chimerios is going to present, and he does this very hands-on via screen sharing into the tool, human exposure assessment of nanomaterials. And in the second part of the session, we're going to have Samuel Harrison and Pantelis Karatsas, who are going to show us environmental assessments. And we're going in both of these tools, look into the tools to really get a clue and understand how they're working. There's quite an extensive list of things that we have on the dashboard, so please take note of the dashboard on top. If you follow the red, click the red button and follow the link, and you come to the NanoCommons powered dashboard for this event. And there you find lots of links that you can get access to the tools that are shown here. You can also see and find examples there and find tutorials and further information. And moreover, we have also installed 2 parallel Zoom meetings, Zoom sessions, where we have some experts waiting for you to assist you in some of the things that we run through. So you can in parallel work on the tools. And when you encounter problems, get there into the Zooms. The links are in the dashboard to get support. Or can clarify any other questions. There is Andreas and Georgia are sitting in one of the breakout sessions in the Zoom link, and Andreas Zumanis is sitting in the other one. So you're very, very encouraged to take advantage of this possibility. I would also like to announce once again, if you are interested in this education and training, we are going to, of course, extend on that. Stay tuned to our working group A on education, training, and communication. Go to the website. I will post the link again and sign in the mailing list. With this, I would like to hand over to Nikos, who by sharing his screen is going to take over and give us insight into the human assessment exposure. Nikos, please.
Okay, thank you very much, Martin. First of all, sorry, it seems that there's something wrong with my camera and I cannot share my video. I do apologize about that. Let me start first with a short introduction of the tools that we are going to see together. Both concern the human exposures in nanomaterials, and we have developed 2 tools, actually. One which is based on multi-box aerosol model, and the other is a dose estimator for human lungs of the nanomaterials. So first, concerning the human exposure assessment, we have developed an application in order to evaluate the human exposure in nanomaterials. So we want to evaluate actually the concentration of nanomaterials in indoor environments. In order to do that, we have the basic, let's say, unit that we have is a room, which we are partitioned to different areas. The basic, one of the basic areas are the near field, or the NF area, which is the location where the source generator exists. The source is where the nanomaterials comes into the environment. The other all areas are called far field and or FFs, and we can have multiple areas. Every area inside the room must be embedded to the larger area, and it can be cuboid or cylindrical. Here, on your right, you can see a simple example where we have a room, and we have partitioned it into an NF, which is inside an FF1 and inside an FF2 areas. So we will see many examples of how to construct such sketches of rooms. Now, concerning the input to the application, we need the diameters distribution of the nanomaterials that characterize the source, that we call the bins, as you will see. And for now on, we can treat many nanomaterials, such as black toner and titanium dioxide. Of course, we have the possibility to create our distribution of bins in the application. For the output, what we will get is the concentration of the nanomaterials per bin per box. Now, this is for the multi-box aerosol model. For the other model, the lung exposure model, we want to have an estimation of the dose of nanomaterials in humans. So in the input, again, we need the diameter distribution of the nanomaterials, but, and if you see that correlated with the aerosol model, we need the concentration of nanomaterials in different areas of the room that we have partitioned. And the output is the deposited dose in these regions of human body. So, concerning the software applications, the multi-box model and the lung exposure model are both developed in Java. The multi-box model uses an Apache Common Math 3 dormant prints algorithm for the time integrations, which make it very efficient. And both applications use ZK framework. Here are the two links that we're going to use. So this is in general a very quick presentation of what we're going to see and interact with, hopefully. So here we have uploaded several documents that we are going to use today that you have access. You can find them here in this link in the NanoSafe dashboard. You can see that we have two tutorials. These are generic tutorials in a sense that they give you instructions of how to use the software in a more generic way. But also we have gathered the examples that we're going to use today. These are exactly what we're going to do. So in case that you want to do something on your own or we don't have many time to do so, you can follow these instructions in order to repeat it. For both applications, the links can be seen here for the aerosol and for the lungs exposure. Let me close my eye. So I press here in order for aerosol to open. And this is the aerosol model for the estimation of the concentration of the nanomaterials. I would strongly suggest, if you want to join me and also try to repeat what I am doing, I will do it rather slow in order to be able to follow me. And of course, we can discuss as long as we work together. So the first thing that you see is the computational domain. Here is where we have to partition the room to the areas that I mentioned, the near field, the NF, and the FF. So in a simulation, we can have, of course, one room, one NF, because there we assume that we have only one source inside this NF, but we can have multiple FFs. For the first example, we are going to use only one FF. So here we can see the areas, the schemas, which can be cuboid or cylindrical. Here is the starting point, which is if we use cuboid areas, it is the lower left corner. But if we use cylindrical, it's the center of the circle. Here we define the schema dimensions. This is actually the dimensions of the area. And this is our flows which connect the boxes, the areas among them, and to and from the environment. So flow to next area is the communication between two areas. And from inlet, it's a flow that comes from the environment inside the different areas. And flow to exhaust is the flow going out from the box, from the area to the environment. So for our first example, I'm going to use here a starting point of 1 for the NF and a schema dimension of 2. For the flow to next area, to FF1 actually, I will put 10. And for the FF1, I'm going to put it as to be the entire room. And this is important because when, in order to have deposition inside our model, to enable the deposition, the sides of the area, for example, the FF1, must coincide with the side walls of the room. So, from practically speaking, if I do this, then you see here that this side of the wall does not match the sides of the wall of the room. So, in this wall, we're not going to have a deposition. So I'll let here. So we take into account that in every wall of the room we will include deposition, and I put here again 10 for the flow to next area, which is actually the NF. This is the other way around, and for the flow to exhaust, I will put 5. And this concludes the computational domain. For our second. Continuing, we need to have a scenario description, which actually is the material that, the nanomaterial that we are going to use to our simulation. In this first example, I'm going to use black toner, although we have plenty of materials to use. And for the simulation input, I'm going to use a value of 300 seconds. This is our modeling time that we're going to solve to integrate the equations. And for the time of source being active, I will put 50, which means that for the first 50 seconds of the modeling time, the source will be active. For the repetitions, I will put 1. I will include coagulation and deposition in our computations, and I will not change the physical parameters. And I will press simulate. So it's rather fast, as you can see. So here are the results. Which first we have to select the area that we want to see the concentration. For example, I can use for this problem NF, and then I can use the bin. The bin is the concentration is actually the diameter, the specific diameter of the nanomaterial. And here you can see directly how the concentration of the nanomaterial in the NF area elapses with time. And you see here that for the 51st seconds, as we put here, the source is active, and then it when the source closes, then the concentration drops. And we can see here also for the FF1 area that as it first increases, and then we have a small drop in larger times. Of course, if I want, I can download our example in a CSV format for in order to further manipulate them. Give me a moment to open my Excel, and I will give you an idea how is this file structured. Okay, so first of all, so we have the input information, which is summarized here. This is because in general, we want to have an integrate all the information that we have used. So this is the input that we have used in order to generate the output, where the output, as you can see here, this is for the near field area, the NF area. Here are the time steps, and here are the concentration of will be active as we will put the simulation. So we will have one from 0 to 50 seconds, and then from 300 to 350 seconds, the source will be active. And this will be clear in our results. So here, if I could put an F area and bin 1, here, okay, you can see here that we have a jump from the first source until 50 seconds, then it drops again, and then it goes up again because the source is active again in 300 seconds. And the overall second. Now, for time, in our other example, we can use again the same computational domain, but instead of black toner, we will use the titanium oxide. You see here, this plot, this graph here is the diameter distribution, which actually, these are the bins, and this is the emission rate that we use in our calculation. So if I go here again, I will put 1, and I will put simulate. Sorry. Okay, it did it. So the execution time of the code depends highly on the number of bins that we have. Titanium dioxide has less bins, has actually 14 bins, half of the black toner. That's why the simulation was faster. And again, I can see the concentration in the different areas. Sorry about that. Here, for that beam, the initial concentration is 0. That's why I get 0. So here you can see again the concentration over time. Now, to other functionalities, I will go back again. Okay, and instead of using cuboid for NF, I'm going to use cylindrical. So the radius, now it says here, and you can see the radius. Of course, the radius is 0. That's why it shows nothing here and only a line here. I will put it to 2. And hopefully you will see. Okay, didn't do it. Okay, we had a small latency. So here you can see that I replaced the cuboid for the NF to a cylindrical one. And I will use black toner again. And I will go to simulate. Okay, and now again, I can see my results. Okay, here you see that there is a more sharp rate here compared to the cuboid one. And for my final example on the aerosol application, I'm going to use 2 FF areas, all cuboids. So I'm going to go here and I will select 2. You see that these were updated. Now we have FF1 and FF2. I will put here cuboid and 2, and here, sorry, and here also cuboid. I will use this input for the NF, so it's 1, 1, 1, and for the dimensions is 2 by 2 by 2. I will put here 0.5, 0.5, and 0.5, and I will use a length of 3, 3, and 3. And I will put a flow to the next area of 10 and a flow to exhaust of 5. And again, my last region, my last area, sorry, it's which is FF2, it will be 4, 4, 4, and again 10 and 5. So I have constructed 3 areas now, for which I'm going to compute the concentrations. I will use again black toner, and I just have to press simulate and wait until I get my results. So now here in the area, you have NF, FF1, FF2, all the areas that we have. I will select all, and for the bin, I will select bin 1. And now you can see here how the concentration evolves over time for our different areas in the different bits. So I don't know if you have any questions about this model, because I'm going to proceed to the lung exposure model, or if you want to gather all the questions after the presentation. Okay.
Yeah, at the moment, there are no questions in the chat box, but I encourage people, put them anytime you want, and we're going to take care that they are going to be answered whenever possible. I put them on display. Thank you.
Okay, excellent. Thank you. Thank you very much. Now, for our other model, for our other application, we have created this lung exposure dose calculator. This is something that we are working on, and some things will be a little bit different. So here, what we want to do is based on the diameter distribution of the nanomaterials. We want and the initial concentration, the final concentration of the nanomaterials, we want to estimate the dose in humans. In order to do such thing, we have 3 methods to do that. One is theoretical, the other is called template, the other from aerosol. I'm going to show you examples from every one of them. Of course, everything is gathered again in the drive link that we have sent you. In the theoretical case, we want to load a DP distribution and to have an estimation of the concentration of the nanomaterial. In order to have an idea of how this DP distribution looks like, we have this box here, which is a DP distribution sample. And if you press it and open it, you will see that it's just a plain file with the values of the different diameters of the nanomaterial. And this is what I'm going to use. So I'm going to use the DP distribution that I just downloaded. This is a very, very simple case where you have a straight line. For the concentration of the nanomaterial, I'm going to use a value of 20. For the exposure duration, a value of 100. For the respired volume rate, a value of 10. And for the density, a value of 100. And I will press the calculate dose. And here, as you can see, I have the calculated dose in these different regions of human body in milligrams. Of course, I can download also the doses for further. This is the simplest case, the theoretical one. We have also the template case. In this case, we have again to provide a D distribution, but we also have to provide a concentration per bin of the nanomaterial. Again, we have a button which you can download the concentration sample. I download it, and as you can see, again, it's just a simple file with a concentration per bin. So if I load again the DP distribution and the concentration per bin. So I will use the same values as here, and I will press calculate dose. And okay, we have again our doses in milligrams. So as you understand, we need, in order for the lung exposure model to work, we need the distribution, the diameter distribution of the nanomaterial and the concentration of the nanomaterial per bin. The nanomaterials concentration per bin is calculated by the multibox aerosol application that we just saw. So what we have done is that we have connected these 2 applications. So this is what is the method from aerosol does. So here, instead of providing any information, I compute it or I take them right away from the aerosol application. So if I press aerosol configuration, it pops up the GUI of aerosol. For this problem here, I will use a value of 111 for the FF, 2 by 2 by 2, and 10. And I will use for FF1 a value of 4 by 4 by 4, again 10 and 5. I will use black toner, and I will left here the default, and I will press simulate. So when aerosol finishes, then it loads up the results. So here you can see the diameters distribution for the black toner that I've used. And this is the final concentration per bin, per nanometers diameter that was calculated by aerosol. And these are the different regions of the boxes as I define it in aerosol. So here, the near field, the NF area is highlighted because this is what we have selected here. But if I want, I can select FF1, the other region. As you see, it was gray out. You will see that the concentration also updated. So I'm going to use an F here. I will leave this values here, and I will calculate those, and I have an estimation of the dose in the various regions of human. So this is what I had to say. I don't know if you have any questions, or you want to see something together, or do another example.
So we have actually one question in the chat, which I put on display if you look in the display. It regards to clearance actually in the lung. So quite an interesting and important issue. How much is this? Is this relevant clearance or not?
Actually, it's for in the lung exposure, we take into account the entire time of the exposure. So if we put in aerosol 600 seconds, then we take the sum of the concentration per bin. That is what we use in order to compute the lung, the dose.
And the question was also whether one can combine different concentrations of repeated exposures.
As it is now, no. Unfortunately, no. But I think we will work on that because it seems it is a very useful functionality.
I do still see that Rosalia is still typing. Maybe there is a question also coming up very soon. Yes, I put it on display.
Yes, thank you.
Translation to in vitro doses.
I don't know about that. I cannot answer.
In the morning when Langtran was presenting, very interesting and important topic, yes.
I have to get back to you about that, unfortunately.
Okay.
I see Andreas is writing something. Probably he has the answer. Okay, yes.
Well, there are a couple of approaches, I guess, pursued currently. Langtran was also mentioning them in the morning. And I guess this is relevant. This is something that, of course, hits into other projects too. We have noticed that. So we have already Samuel Harrison waiting to now drag this further to environmental exposure.
Okay, let
me thank you once again.
Hi, thank you.
Nikos.
Yes, can you hear me?
Yes.
Okay, great. So thank you from my part.
So, Sam,
Hello.
the stage is yours.
Thank you very much. Let me just check that I can move slides, which I can, so that's good. Yeah, thanks. So I'm going to now introduce the environmental exposure side of the NanoSolvit platform, and what we're doing with regards to incorporating an environmental exposure model into the NanoSolvit cloud platform. So this is going to be a two-part presentation. I'm going to kick off by introducing the model itself, which is the nanophase model, and then I will pass you over to Pantelis, who will give a demonstration of the model in action in the NanoSolvit platform. So I apologize, the first part of the presentation, which is me, is not that interactive. I'm just going to give a presentation, but to give some important information about the model. So I thought I'd start with kind of reflecting on the past decade or so of nanomaterial exposure modeling, starting with, well, that's not me moving the slides. There we go. We have a rogue person moving the slides. Starting with why do we need to model nanomaterials? Why do we need nano-specific models to begin with? And why can't we just use conventional chemical models that already existed and make them adaptable and nano-specific? And this all comes down to the fact that nanomaterials, they can form thermodynamically unstable suspensions in the environment, such as heteroaggregates to environmental particles, such as suspended particulate matter. And this means we can't use equilibrium chemistry, and we need to make nano-specific models and tools to be able to deal with this. And accordingly, over the past decade or so, there's been a plethora of different nanomaterial exposure models created of a variety of different shapes and sizes. So we have models of, we have multimedia models, that box type models that give you spatially average distributions in different environmental compartments. And you have models that give spatial and or temporal resolution, usually just in one compartment. But the thing that was really missing from this was a model that offered both spatial and temporal resolution over multiple environmental compartments. And this was the gap that the NanoPhase project, which ended at the end of last year, this is the gap that the NanoPhase project aimed to plug with the so-called NanoPhase, nanomaterial fate and speciation in the environment model. So as a quick introduction, the nanophase model, so it's a spatiotemporal model of nanomaterial fate, speciation, and biouptake in the environment. And it's spatial, so it represents a geographical region by splitting it up into a number of grid cells. And each of these grid cells can have compartments representing the soil profiles and soil layers, and surface waters, rivers and estuaries in this example. And these surface waters can have bed sediments. And so I thought this is a slightly complex slide, but I'm going to come back to this later because it's quite important as to how we get such a complex model into the NanoSolvit cloud platform. But I thought I'd just reflect on what such a complex spatiotemporal model means in terms of the data that are required to run it. And well, the overall picture is that the data required to run it are quite complex. So we have all sorts of different data, meteorological data, land use, soil properties, topography. And a lot of this data itself is spatial and temporal. Some of this needs to be passed through a hydrological model to give us hydrological flows. And then obviously we need information about the nanomaterial itself. So the nanomaterial's phys-chem properties, and how and where and how much of it is released to the environment. And so the general picture here is that such a complicated set of input data generally requires some form of expertise to run the model. And what that means in practice is that often models of this type of complexity are only really ever run by the people that create them. So just to wind back a bit and just to give you a bit of an example of some of the outputs from the model, I'm just going to show you some results for this scenario here, which is running the model for the Thames catchment in the UK using a grid resolution of 5 by 5 kilometres for the years 2000 to 2020 and for nanotitanium dioxide. And this scenario here, this is based on modelled releases. So they're quite realistic releases, spatiotemporal releases of nanomaterials to the environment. And so these are the kinds of questions we can begin to answer with this type of model. So here, this graph on the right, I'm just giving you an overview of the total mass of nanotitanium in the entire catchment, split up by environmental compartments, so soil, sediment and surface water. And then that graph at the top there, that's just giving you the emissions trend, so the masses per meter squared of nanomaterials emitted, just to give you an idea of how the emissions are increasing over time from 2000 to 2020. And the main picture here is that soil very much acts as a sink, and the main term driver to the dynamics in soil are these exponentially increasing emissions. And just to demonstrate that stuff is happening in the other compartments, this is the same graph but logged, and you can kind of see that in waters and in sediments, nanomaterials are increasing in mass over time, but not at as high a rate as the soil compartment. So it's a spatial model, which means that we can produce maps, we can produce spatial distributions of nanomaterial concentrations. And this heat map here is a map of the Thames catchment, and each of the grid cells represents the concentration of nanotitanium dioxide in soil at the end of 2020, so at the end of that 20-year model run. And the colour of the grid cell represents the concentration, and the more yellow the grid cell, the higher the concentration. And so you can see here clearly that the urban areas around London specifically have lower concentrations of nanomaterials and soils, and the areas outside, the more rural areas, they have higher concentrations. And this is down to where nanomaterials are emitted to the environment. So the main way which titanium dioxide gets into soils is through the application of sewage sludge, which obviously only happens on agricultural land in rural areas. And so we can say that the main determinant of the spatial distribution of nanomaterial in soils is land use. So soil isn't that dynamically interesting in terms of nanomaterials. So I thought I'd just reflect on a slightly more dynamically interesting compartment, which are surface waters. And this example here, I've picked out two reaches, a river reach and an estuary reach, that are kind of representative of the whole catchment, just to give you an idea of how nanomaterial concentrations change in these compartments over time. And again, I've just given you the emissions trend at the top there to give you an idea of how nanomaterials are being released. So the main conclusion here is that the main driver, particularly in rivers, to nanomaterial concentration is the hydrological flows, rather than the emissions trend, which is why you have these big peaks, which coincide with the summer months when the flows, the river flows, are low. Estuary is a slightly different picture. Obviously, it's quite noisy, and you do have these peaks and troughs, but that you can kind of see that there is a bit more of a trend in line with the emissions trend there. And that's down to the fact that, well, estuaries waters can go upstream and downstream, and this upstream flow acts to dampen the net downstream flow of nanomaterials, and it basically traps them in place a bit, which it gives them a bit more of an opportunity to build up. Hence, you're seeing them acting slightly more as a sink. Okay, so just to reflect on this, how this type of model is generally used and how useful it is for regulation. So as I've already said, it's a complex model, which means that it's not easy to use. It needs experts to use. And so you'd only really ever use this in a regulatory context as a last step. So if you'd already gone through some kind of tier approach where you had done some simple calculations to determine the risk to the environment, and if those calculations came out saying, oh, actually there might be a risk, and those calculations would be as conservative as possible. So that's on this graph here, that's the lower tier. You then might move on to a simpler model like SimpleBox for Nano, which again is conservative by nature, but is a bit more realistic than your simple back of the envelope calculations. And then if this intermediate tier model, SimpleBox for Nano as an example, indicated that there might be risk, then you might consider moving on to a higher tier model, a complex model like the nanophase model, to give you as realistic a picture as possible of how nanomaterials are distributed in the environment. And so this kind of made us ask the question that motivates a lot of this work in incorporating the nanophase model into the NanoSolve cloud platform, which is, well, what if we can simplify the model inputs such that we can create a GUI that makes this complex model as accessible as possible to non-modelers, regulators, industry. So I just want to quickly come back to this slide. So when we're thinking about how to do this, we kind of realize that, well, actually, a lot of the complicated information, the spatiotemporal information, can be broken off into what we call a geographical scenario. It's stuff that represents the geographical region that you're modeling, like the hydrology, the soil. And actually, we can fix that. So we can give users a geographical region in which they are able to model. And that means we can abstract away a lot of the complexity of the model. And so this means that the only things that the users need to define then are the characteristics of the nanomaterial itself and their emissions to the environment. And in fact, we can abstract away the phys-chem properties of the nanomaterials by giving them a predefined list of nanomaterials that they're able to model. And then the only thing that they're left to have to do then is to define how and where and how much nanomaterials are emitted to this fixed geographical region. And then I've focused a lot on the data input here, but just to say also, I mean, the model outputs either netcdf or CSV files, which are not very user-friendly, but obviously a great advantage of having a user interface is that you can then visualize the outputs and as user-friendly a way as possible. And hopefully that's set the floor nicely for panelists now, who I'll hand over to give you a demonstration of how that works in practice. Over to you.
Perfect. Thank you, Sam. I hope now that you are seeing my screen. You can find the available links for the application at the Training Day dashboard that is created for this meeting by pressing at the nanophase cloud NanoSolve EU. Someone will be guided to the landing page of the application. The first thing someone has to do is to log in to the application or register if not already a user of the tools that we are creating. So after the login, the page redirects the user to the catchment of themes that it is already modeled and integrated into the application. Each user has its own list of emissions, scenarios, simulations that can be shown up on the map, as we will show in a while. And some other actions that can be done upon the map is entering a polygon, a point, zoom in, zoom out to the map, and change to the theme that he likes more and have a better representation of the results. So we are here at the themes catchment. The first thing is for someone is to add emissions upon the map, as Sam mentioned earlier. So one can add an aerial emission by creating a polygon where the emission is happening. And when the polygon is closed, the data of the emission are entered. you have to enter the nanomaterial, which is the dioxide of titanium. Let's say that this specific emission happens on soil with pristine form, and let's say that the emission consists of 1 kilogram per meter square per year. So, as this one emission could already be an input for a simulation, but a more realistic scenario would probably consist of more than one emissions. So, let's add, for example, another emission, a point emission. Again, by adding all the required values. And again, 1 kilogram per meter per year, save. So, right now we have 2 emissions on the map, and we can further continue adding more emissions if needed in order to create a scenario. When emissions are shown on the map, we have a button here which let us store these emissions in a scenario. And when these emissions are stored as a scenario, the button changes from save to run. And this is available whenever a scenario is shown upon the map. Let me show again something. I can go upon the emission and change, remove from the map and do whatever I want. Then again, I have one emission which is not stored in a scenario, so I can save again a scenario. Now I don't have anything, so I don't have a save. I have the scenario, a personal scenario list that the user have created. So then again, I can use again that scenario to run the simulation. So when the scenario is presented upon the screen, then I can go on and create a simulation. I just add the simulation name, the simulation description that I would like to have, and I'm choosing the start date for the simulation. The simulation outputs will be 365 days of simulation upon the specific catchment. So let's say that the simulation will start at the 1st of November. Now I have the start date of the simulation, and I can continue with and I can press the run button, which will create me a simulation. After that, the simulation will be available and running, nanophase simulation, as we see here. And I can see the simulation. It takes a lot of time for all the data to be crunched and create a useful schema, a JSON schema that we need in order for the GUI to be able to render the simulation outputs, also to be stored on databases and get all the results through the API. So someone should have a little patience in order to see, to start seeing some models, some outputs. In order for the demonstration, we have created a simulation, and every simulation has its own URL. So this URL is also shared with you through the dashboard, and so by clicking one can see the outputs of a simulation. So the outputs are grouped into 3 categories. One can show the outputs for the water, and I'm pressing water and I'm choosing now that I would like to see the water, and I would choose then the output day. By clicking on this line here, I choose now the 31st day of the simulation. On the map now I have rendered some points, and when I click upon a point, I can see all the simulation outputs. I see the time, which is the 31 day, a date time, some features that depends upon the output, and then I have all the values that I need in order to get further understanding about the simulation that we have created. So the first thing that we want to notice upon that, this is not the most user-friendly output rendering, but we have the values needed in order to continue further down with further integration with kinetic models and other hazard models by using these values as input to these models. This version of the application is a beta version, and right now we are working on better interpretation and rendering of the models, and the final output will be something like that, where a more reactive rendering will be available for the end user in order to see the concentration of the nanomaterials due to the simulation and upon the whole catchment that it is available right now. The same applies if I choose a soil output, and again I can see the values that concern the soil outputs. Also for the simulation, I can see the simulation's emission, and I can click upon them and see from where everything started. Right now it is this little dot behind the bigger dot of the layer that renders for us all the outputs. So basically, this is the application state right now, and more features will be available and make this application more easy for the end user to use and get a better understanding of how the nanomaterials will be distributed in catchments around the world. We hope that this application will be extended and integrate more catchments around the world. And that's basically what we have to show you until now. So any questions, of course, will be full.
I'm looking into the chat box. I do not see any further questions so far, but I would like to encourage attendees again, put questions into the chat box and we put them on display for the presenters. All three presenters of the past session are still here. You can also put questions to Nikos, Sam, or Antelis regarding the human and environmental exposure models that were presented. Please also feel free to consult the additional information material which is provided on the dashboard. Presenters were referring to it during the presentations too. So tutorials, links to the models.
Mm-hmm. I'm also posting to the chat the simulation for anyone who would like to interact with the application.
Thank you very much, dear three, for presenting this. There is still, now we are having a break, 10 minutes, but presenters are still around, so you can still, of course, interact via the chat box.
Mm-hmm.
And we are going to start with the next session in 10 minutes. This is going to go into advanced cell culture models. I leave the room again open until then, so interaction can take place. Presenters are still able to answer questions if there are some coming up and are presented to the public chat box. So we are back after our break. It's 20 minutes to Central European time. And we're now going to have an extensive session on in vitro cell culture models, advanced in vitro models of the human lung, of the GI tract, of liver for hazard characterization. And this is going to be run by Kirsty Meldrum and her team. The presenters also extending to Barbara Drasler, Rui-Wen, Angela Kämpfer, Samantha Victoria Llewellyn, and Marije Niemeijer from the Petros project. I guess Kirsty is going to start, and I will shortly upload or launch her film, which she provided, and she will probably introduce the entire team herself. So I give the floor to Kirsty. Please start with your presentations, and I will try to assist you as best as I can by uploading our presentations. We can, however, not give a microphone to each of you at the same time. Otherwise, we're going to exceed the number of possible talkers at the same time. So, Kirsty, you may unmute your microphone.
Yes, hiya.
To introduce your session, please.
So yes, thank you for that introduction. So our session is all about the different models we've developed within patrols. So we'll have a section on lung models, liver models, and GI tract models. And to start off is my presentation on the lung models that we've developed in Swansea. Very much to the organisers of the conference for allowing patrols to present the work we've completed on developing new advanced tools for nanosafety testing. We appreciate being invited to discuss the new models we've made. My name's Kirsty Meldrum, and I'm going to be presenting on behalf of Swansea University and the models we've made with the lung, specifically on developing an advanced in vitro alveolar human lung model. So the lung is the primary exposure route for nanomaterials, especially for occupational exposures. It's the important organ for respiration, and this is what gets oxygen into our blood. There's three main areas of the lung: the upper, the middle, and the lower. And these three different areas are made up of various different cells, which is what we've then focused our models on within patrols. An additional factor to consider when deciding what region of the lungs to study is what size of particle you're interested in, and therefore the area within the lung it'll deposit. The smaller the particle's diameter, the lower down the lung it has the potential to deposit, and therefore the lower down the lung you should focus your work on. So this diagram here indicates the different sizes of particles and the different regions of the lung that they would potentially deposit within. So the top is the pharyngeal and the upper airway. The green is the bronchial area and the middle of the airways, and the red is the alveolar unit that the smallest particles would deposit within. The area of the lung that we've decided to focus on within Swansea University is the alveolar region, and this is the region that gas exchange occurs within. This region is made up of type 1 epithelial cells and type 2 epithelial cells. The type 1 epithelial cells cover around 95% of the internal surface of the lung and are there for gas exchange, while the type 2 epithelial cells are the secreting cells. There are also alveolar specific macrophages present within the area. University, we had 3 different cell types that we wanted to focus on to make our alveolar cell model. These were A549 cells, small airway epithelial cells, which were primary cells and not a cell line, and NCI H441 cells. These are all type 2 epithelial cells. So the first thing we wanted to do was to culture and characterize these cells. So we cultured these for a total of 14 days. These were grown both in submerged cultures and air liquid interface cultures. So initially we grew them in submerged cultures for 7 days, before then switching them to an air liquid interface for 7 days, which is where we took the apical media off of our transwell inserts and just left the basal media. We then characterized these models and we looked at cell viability and cell count, the membrane integrity, and this was done using TIR and blue dextran, and looking at various cytokine and chemokine releases, specifically IL-6 and IL-8. This led us to deciding what cell type we would then carry forward. We did not get on with our small airway epithelial cells. We couldn't get them to grow in our transwell inserts, and this was a massive hurdle for us. But also, our NCI H441 cells have an embargo on them, which means they cannot be used in industrial settings. So therefore, within this Patrols project, we took the A549 cells forward onto our next steps of nanomaterial testing. So this looks like a lot of data. However, the key take-home message from this data is that when you build a model, you need to understand over time how they grow and how they behave. It's important to understand when the optimal time would be to switch them to an air liquid interface, as well as when your exposures should be completed. So with our A549s, we decided that it was 3 days submerged culture growth and 1 day at an air liquid interface before we would expose them to our nanomaterials. And this region is highlighted with these red boxes within our graphs. And this would just give us an indication of when was the most optimal time our model was the happiest for us to complete our exposures. So, building the model. This is a quick overview of what our end A549 and macrophage model looks like as a cartoon. So we have our A549 cells in the blue and our macrophages in the purple. And I note that all of our components are pre-warmed to our 37 degrees before we're using them. So this is one we made earlier, and this is what we're aiming for our model to look like. Our A549 cells come from ATCC, and we grow them in RPMI media, which is supplemented with penicillin streptomycin, 10% FBS, and 1% L-glutamine. We use inserts from Falcon as well as companion plates also from Falcon, and we use a mixture of 12-well and 6-well inserts depending on the endpoints we want to look at and focus on within this project. So initially, we want to seed our A549 cells alone into the transwell inserts with media both on the apical and the basal side, which is indicated by the red on this diagram. So we start by taking our transwell inserts out of their sterile packaging and placing media into the basal side. Now the volume of media you place into the basal side depends on the insert size you're using. For a 6-well insert, it's 3 mils. For a 12-well insert, it's 1.5 mils. We then take the transwell inserts using tweezers and being careful not to touch the membrane with any fingers or any other objects within the hood, and place them into the wells. We then ensure that our membranes are within the grooves within the plates, and then place these into the incubators ready for us to seed onto them. So the next step in seeding and building our model is to trypsinize our A549 cells off of the flasks they've previously been growing and then seed them onto our transwell inserts. These flasks are washed 3 times with PBS. For a T75, we tend to use 10 mils of PBS per flask. And we wash this to ensure there's no media residue left within the flask so the trypsin doesn't work. We then take 5 mils of our trypsin, which again is lab specific, and there are other laboratories that use a smaller volume, and place it within our flask. This is then placed into the incubator and left to incubate for 5 minutes taking a constant looking at the cells to ensure that they've been trypsinized properly, and then taken back to the hood. So now that our cells have been incubating for 5 minutes in the incubator with the trypsin on, we now need to neutralize it. So all the cells have detached from the bottom of the flask. We neutralize the trypsin by adding 10 ml of FBS media into our flask and swirling around to ensure that all the trypsin has been neutralized. We then pipette this into a centrifuge tube and take it to be spun. Once we've obtained our cell pellet, we then pour off our waste media and resuspend our cell pellet in a mill of media. This is done gently as we don't want to disrupt the cells or kill any of the excess cells. We then calculate how many cells we need for our seeding, and we dilute our cell pellet as required. Then, taking the plate from the incubator, we seed 500 microliters of the cell suspension onto each apical side of the membrane, if it's a 12-well plate, and 1.5 ml of this if it's a 6-well plate. The next step of our model is to prepare our macrophages. There are other macrophages that you can use, as well as different differentiation methods. However, within Swansea, we use THP1 cells and we differentiate them using a PMA method. This differentiated method has been characterised within the university and within the group. As I've said previously, it's important to know what you're working with and what the cells are like once they've been differentiated. You need to understand the cells before adding them into a pre-characterised model. So we seed our cells at 1 × 10⁵ cells per mil, and we add 20 nanomolars of PMA for 48 hours. We then change the media to fresh media, and we allow this media to be on for 24 hours before removing the macrophages from the flasks, seeding them onto the transwell inserts, and having them in an air liquid interface for 24 hours before doing our exposures. So 4 days after we have seeded our A549s onto our transwell inserts, they are then ready to be switched to an air liquid interface. So we remove our apical media and we change our basal media, so the media on the bottom is fresh. 24 hours after switching our differentiated THP1 cells to media, we then repeat our washing steps as we've seen previously with our A549s. So we wash our THP1s 3 times with PBS before adding 5 ml of Accutase onto this. Now, we use Accutase instead of trypsin as it's a gentler method and it works in a different way. We incubate this for 10 minutes within our incubator, and once it's been incubated and the majority of the macrophages have detached from the flask, we neutralise our Accutase using 10 ml of our cell culture media. This is double the volume of the Accutase we would have placed into the flask. We resuspend our, we centrifuge to obtain a pellet. We then resuspend and count our pellet, and we dilute our cells to the 1 × 10⁵ cells per mil we require for our transwell inserts. On a 6-well insert, we pipette 500 microliters of 1 × 10⁵ cell suspension onto the apical side of the membrane. Once we've pipetted this 500 microliters onto the apical side of the transwell membrane, we then allow 2 hours within the incubator for the THP1 macrophage-like cells to adhere to the A549 cells. After this 2 hours, we then remove our apical media and the model is switched to an air liquid interface, so there's only media on the basal side. This model is then allowed 24 hours to accumulate and acclimatise to the air liquid interface conditions before using for any exposures, be that chemical or nanoparticle. The bottom 2 images on this slide actually show a macrophage on our epithelial cell layer. So from the cartoons above, we can actually then see a physical representation of the macrophages on the cell layer. So the right-hand side is a TEM image, so a transition electron microscopy image, whereas the left-hand side was done with our confocal microscope and fluorescent staining. So we can see that these macrophages actually adhere to our epithelial cells as we'd want. Now that we have our model and we've allowed it to acclimatise to the airlight interface for 24 hours, there are various exposure methods that we can implement. The traditional and most commonly used exposure method is a submerged exposure. This is where the whole of the apical side of the membrane is filled with media with our chemical or particle of interest and exposed to the cells that way. The next method, which is slightly more physiologically relevant, is the quasi-alley exposure. This is where a specific volume of media is placed onto the apical surface of the membrane, but does not cover the whole surface, and therefore is quasi-exposed to the membrane. The next two exposure methods are more advanced and again try to replicate more of a physiological exposure method. This is both the dry powder exposure and the liquid aerosol exposure. These have now both been obtained by Swansea University, and we look forward to actually implementing them within our work. So this is an example of one of our exposure methods, which is the Vitrocell Cloud 12. I've placed a QR code on the left-hand side in case anyone would like to have a look at more of the details on the website. So using this system, we place a specific volume of our nanomaterials in suspension into the nebulizer, which is then nebulized into our exposure chamber and onto our transwell inserts that are placed in the bottom of the chamber. We can also then measure the deposition of these particles using a quartz microbalance. This means that we can replicate these conditions quite consistently and are also doing this as part of the Patrols project within various different labs, comparing the deposition we get of specific nanomaterial using this system. So as you can see within Swansea, we focused on the 8549 and differentiates THP1 cell alveolar models. We have focused initially on the quasi-alley exposure method, but are now starting to use our Cloud 12 aerosolized exposure chamber. So thank you very much for listening, and I'd like to invite any questions.
So I do see there's a few questions in the box. The first one about the PMA differentiation. Yes, there are quite a few different protocols for differentiation of the THP1s. And as I said in my presentation, the reason we went with the protocol we did is because it's being characterized in-house. We characterized a range of differentiation periods as well as the concentrations of PMA. And this is what led us to decide to choose our 48 hours with PMA and 48 hours without. For another project we're doing within Patrols, we're actually using a 5-day differentiation protocol for the THP1s with a 3-day recovery phase. So we are using different exposure methods within Patrols, but for this model, it's a 48-hour PMA exposure and then a 48-hour recovery period. On the basolateral side, no, not within this project. We have been looking for seeding endothelial cells onto the basal side of the transwell, but we've only been focusing on the apical side just now. And the pore size we use is the 3 micron pores, but for other cells, they'll need the 0.4 micrometer pores. No, we've not used the machine for printing our compounds on top of the cellular layer, but I think I've seen publications that have done so. So I bet it is fantastic. I would quite like to have a shot with it. So with our primary macrophages, we have got other people within the lab that have been using our primary derived macrophages from blood. Within Patrols, we decided to stick with our cell line just purely for reproducibility and ease, especially now that we are struggling to get hold of blood, with people being a little bit more cautious about donating blood and getting access into hospitals. So we've just stuck with our cell lines, but I know other people within the lab have used the macrophages derived from monocytes, and within patrols, it's also been used within other partners. So that ratio is based on a previously published literature as well as historical data that have been produced by different labs, the ratio. Yes, exactly. So Barbara is going to show the primary monocyte work. So with the A549s, we actually struggled to get a tier value that would replicate what we read in literature. The tier value we got was maybe a factor of 10 lower than what we read in the literature. But this was actually consistent between ourselves and another patrols partner. So we weren't sure if in the literature it's reported differently, if it is, say, centimeters squared, or if it's just a tier value. But we struggled to get quite high tier values with our A549s. With our H441s, we did get higher tier values. However, due to the embargo on these cells, we didn't want to take them any further forward. The protocol is being put together now. We're also going to be publishing a paper on this protocol, which should hopefully be with the publishers soon. That's a very good question. Also, one of our other patrols partners has been looking at the Halby cells instead of the A549 cells. Not within Swansea, we focus purely on the A549 cells.
So I guess this statement of Tommaso belongs to the printer.
Yes.
Question, I guess. Okay, thanks a lot, Kirsty. I guess we are going over to Barbara. Barbara's talk or presentation I will upload shortly.
Sure.
On inflamed alveolar epithelial model for nanomaterial hazard assessment. Thanks
All right. Okay, thank you very much. Sorry.
Thanks a lot for coming. The stage is yours.
Thank you. All right. So thank you, Martin, for the presentation, and to you, Kirsty, for giving the introduction on the lungs and its compartments. So I will also present an alveolar model. It's a bit a different one than Kirsty presented, and I will present how to prepare a diseased, inflamed model in vitro. I come from the University of Fribourg in Switzerland, and we are also part of the Patrols project. So as I said, I will focus on the innermost, the deepest regions of the lungs, and these are alveoli. And as Kirsty said, this is where the gas exchange occurs. That's why this is a very important region. We can mimic this alveolar model again by using these transfer membrane inserts and by seeding different cell types onto it. We can use then the cell culture medium so to serve as the circulatory system in terms of to bring the nutrients to the tissues. And importantly, those transfer membrane inserts enable us to cultivate the model at the air-liquid interface, which is for the lung compartment very important. So preparation of the model starts with isolation of primary blood-derived monocytes. So we obtain those mononuclear cells by purifying the blood samples that we obtain from regional transfusion centers. So we purify those samples using a cell density gradient. After this, we obtain, you see my cursor or not? Yes? Oh, all right. Just I'm trying to get the cursor.
If you want to highlight something, you go to the bottom At the third button from the left side, you see your cursor, and you can select, for example, the pencil to draw things.
The pencil, all right, I have it. Thank you. So here we can see this buffy coat. This is a layer of white blood cells, which comes after the radiation separation, which comes just below the plasma and above the the platelets and the red blood cells. Then we use magnetic separation cell sorting, anti-CD14 magnetic beads, so to obtain from the sample monocytes. These are the CD14 positive cells. And straight after the isolation, we start with differentiation of the two immune cell types that we're using in the model. And these are macrophages and dendritic cells. We cultivate them in specific growth factors in the medium for 6 days. And already during this differentiation period, we start seeding our epithelial cell line. So also here we selected A549s for this model, and we seed them on transwell membrane inserts, and we wait until they form a monolayer like this. On the day 6, we then assemble the co-culture by adding differentiated macrophages on top and dendritic cells at the bottom of the system. Importantly, we cultivated this, as I said previously, at the air-liquid interface with the aim that those epithelial type 2 cells, which A549s are, that they produce surfactants. This is very important, especially when investigating effects of inhaled materials like nanomaterials onto the tissue barrier. But I want to point out that also other cell lines can be here included, or cell types, also like HILV. Yes, we tried, and also bronchial cell types. But then we just need to make sure that we consider all the cell type specific properties then. I would also like to stress out that for this isolation and differentiation of primary human monocytes, we have now optimized the protocol so that we freeze directly the monocytes. We freeze them, and then when we need them, we thaw them and we differentiate them into the two immune cells. And this very much facilitates the experimental setup, so to not to always depend on the regional transfusion center. So this is now the model from a closer look. We can see A549s in the middle, macrophages on top, and dendritic cells on the bottom. I want to point out here that this is the model that is this is a very powerful tool to investigate effects of different compounds from either deriving from the apical or even from the bottom part to the model. But this model does not represent the airway blood area, because for this we would need endothelial cells, meaning the cells that present the blood vessel cells. So with this model, we do not specifically study transport of the compounds through the airway blood barrier. However, we still consider that cell culture medium is our source of nutrients. So yes, it brings the nutrients to the model. And also the model then secretes, all the cells secrete cytokines and other markers in cell culture medium, and then we can evaluate this from this medium. Here is just an insight into the immune cells that we use. I wanted to show you how macrophages and dendritic cells look under phase contrast microscope after 6 days of the differentiation. And we can also see that when we render confocal images, that pre-stained macrophages and dendritic cells are very nicely integrated on the model on top of the gray epithelial cells. All right, so all the experimental details are presented in our recently published paper in JAVE, and all along with the video where experimental details and especially those tricks and tips are presented in the video. So if you're interested, I would very much welcome you to have a look at the video, and then you can also drop me an email if you still have any specific questions. So now we have the model, and we will come back to it shortly. But before that, I would like to a bit touch the theory about inflammation. So as I said at the beginning, I will present a diseased model, inflamed model. So why is alveolar inflammation so important? Either chronic or even acute inflammation, it occurs in a variety of lung diseases, such as in fibrosis or in chronic obstructive pulmonary disease. And it's important because when alveolar tissue is inflamed, this really impairs the gas exchange in the lungs. And this then also affects that less of the oxygen or not enough oxygen might be derived to other organs. Inflammation occurs as a consequence of a stimulus or a combination of stimuli in the lungs or in the whole tissue, in the tissue. And an example of such stimulus is LPS, lipopolysaccharide. This is a component of gram-negative bacterial cell wall. And also in vitro, we can use this compound to mimic inflammation. But I want to point out that just the presence of stimulus in the tissue, it does not always mean that the tissue will be inflamed. There is first a series of reactions that occurs, and this is called the pro-inflammation, which is the state of alert in the tissue, and the most significant characteristic of the pro-inflammatory cascade of events is relation of pro-inflammatory markers. For example, such as chemokine interleukin-8 and tumor necrosis factor alpha as the main inflammatory factor, or IL-1 beta and many others. And in vivo, this also means that such a state attracts then immune cells from circulation so that they come at the site of infection, so in alveoli. So as I said, in vitro, we can also use this tool. And if this stimulus LPS, and if we're lucky, then our model will respond to it by showing pro-inflammation specific characteristics. So how to include this in our experimental setup? After the model had been at air-liquid interface for 24 hours, we can challenge it with LPS. And we optimize this in our work so that LPS can be applied either from the apical side or from the basal side of the model. So if we start with the apical side, so this means from the top of the model, we apply LPS only as a thin layer of dispersion on top of the model. Why is this important? So that this liquid really evaporates so that air-liquid interface conditions are preserved. Again, I'm pointing out in lung research, this is very important. This type of LPS or inducing inflammation with LPS comes in very handy when we want to test some therapeutics that we would deliver in a medium, so to resemble a therapeutic being delivered from circulation systemically, because we would like to avoid a contact or possible interference between a stimulus and the investigated compound. On the other side, when we apply LPS from the basal side in the medium, this comes in handy when we're testing, for example, respiratory hazard of materials, which we're interested in today. So for this is good because then the materials we would apply directly from the top, for example, as Kirsty presented, using an aerosolization system. All those details and about the meaning and the methodological steps how to induce both the types of inflammation are presented in our recently published paper, and please just contact me if any additional information would be required. So regardless of the approach, an inflamed tissue has its specific features. So one thing that a pro-inflammatory status in the tissue does is that barrier integrity is compromised to a lower or higher degree. A compromised barrier integrity can be visualized using confocal microscopy, for example, or also using permeability tests such as fluorescein or even TR, as we discussed before, but not for A-fibronase. And as I mentioned before, a very general characteristic is secretion of pro-inflammatory markers. And we can assess this with ELISA, and we can also do the respective gene analysis with PCR. Also, various other endpoints can be or are even advised to be more monitored in parallel, such as cytotoxicity, oxidative stress, and many others. But with this, I will not go into details. So as a first thing, I wanted to show you that basal site of application, meaning applying LPS in the medium, creates a more prominent pro-inflammatory conditions in the tissue. It makes sense because this really resembles a systemic inflammation. We can see here with those white circles in the middle panel that applying LPS for 24 hours in the basal compartment, it creates those holes in the tissue, which we can see here, where cells are marked, actin is marked, cytoskeleton in pink and nuclei in blue. And we can see that these are here some empty spaces, which are less prominent when LPS is added to the apical site. And here nicely, we can also see at some places macrophages that are colored in white, and here is one dendritic cells that is green. It's a bit faint, but it is there. And then also, as I mentioned, we can use cell permeability assays. So here we use the labeled dextran. And we can see where LPS is applied in the apical, in the basal site. This is marked with 1. We can see that the effect of cell layer permeability was comparable to the one where we use EDTA as a positive control. Whereas when we applied LPS apically, this was much more similar than to untreated cells. As I mentioned, also cell viability is good to be tested, and we can see that both the approaches actually did not cause any impaired or did not induce cytotoxicity, which is good because we want to measure the events before that. So we don't want LPS to really be toxic at the end of the day. And then we also tested secretion of pro-inflammatory markers. Here I'm showing an example of IL-8 and TNF-alpha. And we can see that with both the approaches, there are elevated levels of those proteins secreted and also of the genes, of the respective genes. We cannot really say, and it was not statistically significant, that the approach 1, this means when applying LPS in the basal compartment, would trigger a higher response, which is okay, good, because it means that also when LPS is applied apically, it actually works. Both the approaches work very well. So now we have an inflamed model, and now it's ready to exposures to nanomaterials. So this is something that we have not yet done in the lab, but it is on our to-do list in the group. So this means that after we have the LPS challenge, the LPS is applied in the system, for example, in the basal compartment for 24 hours. We would then here do the tested material. Here would be the exposures on the day 9, and then, for example, on the day 10, which would be 24 hours of exposures to a nanomaterial in an inflamed model, we would then do sample collection and data analysis. I would personally recommend that LPS here throughout the period would stay in the system because this would more realistically mimic the conditions that we have in the lungs. So once we have a systemic inflammation, if we don't get the treatment, most likely it will not faint very fast or go away very fast. So here I'm coming already to the end of my presentation. So What I presented today is that we can, in 10 days, we can assemble the model from primary immune cells and a cell line, and we can induce inflammation and expose to nanomaterials. And of course, we need to analyze the whole thing. And I want to point out that LPS is a very good pro-inflammatory stimulus for such a model in vitro. And the main characteristic of pro-inflammation can be then tested with very widely accessible tools such as confocal microscopy and permeability tests for impaired barrier integrity, and then ELISA and PCR and other bioanalytical techniques for the other markers. With this, I would like to thank my supervisors at the University of Fribourg and the whole Bionanomaterials group. And I would, of course, like to thank the Petrels Project's partners and the funding for all the support. Thank you for your attention, and I'm happy to take any questions. Yes, the link to the video, I can post it after I finish all the questions. I will post it here in the chat. Is that all right? Yes, okay. We had a look at CD86 only, but not 54, thank you. But we had a look at CD86 only in monocultures. We haven't optimized flow cytometry approach yet to the whole triple co-cultures because it gets quite complicated. But thank you. Okay, interesting question about the surfactant. It might be, but it's also the fact that it's much more LPS, like the nominal dose is higher. But might be that that surfactants do protect from LPS from the top. It might be. However, I think LPS is quite soluble, so it should also go through the surfactant and come to the cells. I think so. For confocal microscopy, we fix it with PFA, and then we stain with immunofluorescence dyes. I can send you the link to the paper where we describe it, but it's quite a simple approach, or the widely used approach. Yes, I see now. Yes, all right. I do agree, might be. Good point, thank you.
Well, we saw quite a couple of questions. Thank you very much, Barbara.
Thank you.
Happy now to add on to Rui-Wen. And I will quickly upload the presentation. Regards to optimization of an air-liquid interface co-culture model to estimate the hazard of repeated aerosol exposures. So please, Rui-Wen,
hello.
Continue with the presentations. Thank you very much.
Okay, hello everyone. My name is Rui-Wen from IVM in the Netherlands. Today I'm glad to introduce the optimization of an early cell co-culture model for aerosol exposure. As we know, human bronchial epithelial and alveolar epithelial cell models are both options for in vitro experiments, especially to ultrafine particles, since both of these two regions can receive ultrafine particles on their surface. As the two presenters introduced the alveolar cell models before, today I'm glad to introduce one co-culture model. Oh, sorry. I'm glad to introduce the optimization of an epithelial plus macrophage co-culture model under early conditions. And then I will show the application of this co-culture model for early exposure to nanoparticles. Here are some backgrounds. as we know, the inhaled particles can deposit onto the long branchial epithelium. So our study focused on the long branchial epithelial cell models to evaluate the inhalation exposure. To closely mimic the inhalation exposure, the early culture and early exposure were developed. So during the early exposure, the cells can be directly exposed to the various substance. It's real-time exposure, and there is no loss during the exposure, and it's also what happens in our lungs. But if we want to do the early exposure, the cell selection is necessary because not many cell types can remain viable for long-term early culture. In our studies, we selected color-3 cells, 16HB, A292, and BIS2B cell lines for testing. As the epithelial cell for the epithelial cell models, the barrier function and single-layer morphology are essential criteria. So we measured the TR values of these cells and also did the Llewellyn protein stainings. For all of these cells, the cells were cultured under submerged for 7 days. Afterwards, we removed the apical side medium, and then the cells were started to cultured under the early conditions. So from these results, we can see only the color-3 cells can maintain the monolayer structure and keep a strong tight junction under long-term early culture. Oh, sorry. I lost the screen.
So we have.
Oh, sorry. Oh,
but he is here.
yeah, I'm in. Or can I?
Please
keep
continue.
going? Hello.
Yes, please continue.
Okay. Okay. Sorry. I lost the signal. So from the results, we can see only the color-3 cells can maintain the monolayer structure and keep a strong tight junction under long-term early culture. Also, the macrophages play an important role in uptake and clearance of particles in our lungs. So to evaluate the realistic responses to particles, the co-culture models need to be created by adding macrophages on top of the epithelial cell layer. In our study, to build the Cal3 Cal3 plus MDM co-culture model, we first differentiated the macrophages. We first differentiated the primary monocytes to macrophages by adding the MCSF. Afterwards, the differentiated macrophages are added onto the Cal3 cells layer for several hours for adhesion. After removing the apical side of the medium, the co-culture models are ready for testing. But during our experiment, we found the macrophage adherence time and seeding concentration can affect the monolayer structure and sensitivity of co-culture models. In our experiment, we tried the different time points and seeding density for macrophages adhesion. We found a long-term period, for example, 24 hours, with medium on top of the monolayers, can affect its structure. So to avoid this negative effect onto the monolayer, a short adhesion period, for example, the 4 hours, should be used. However, the efficiency of macrophages adhesion decreased with a short adhesion period, then decreasing the sensitivity of co-culture models. To make it balanced with our optimization, we decided to use the seeding density at 50,000 macrophages per square centimeter at the 4 hours adhesion. We also did the mutual comparison between Cal3 monoculture, Cal3 MDM, and Cal3 TDM models after exposed to LPS. So from the results, we can see the Cal3 MDM model shows the higher sensitivity in inflammatory responses to LPS exposure. Next is the application of Cal3 MDM model. We use this model for a single day exposure to nanoparticles, DQ12, with the early exposure system. So here are the information of the parameters. So after exposure, we found the Cal3 plus MDM co-culture showed the cytotoxicity and the inflammatory responses to DQ12 exposure. But in our parallel experiment, the cytotoxicity and the inflammatory responses was not induced in Cal3 monoculture by DQ12, and the repeated exposure experiments to DQ12 and other nanoparticles are still ongoing. So based on our results, we can draw some conclusions. Cal3 MDM co-culture model had the epithelial monolayer integrity on the long-term early culture, and it showed the increased sensitivity in response to LPS and DQ12 exposure. Therefore, Cal3 MDM co-culture model is a good option for early exposure to aerosols for toxicity testing. That's all. Thank you.
Thank you, Rui-Wen.
Yes, thank you. Sorry for the
was just a transient one, and you could come back with your presentation. Do we have some questions? At the moment, I cannot see questions in the chat box.
Okay.
So I thank you again for the moment, and I will give the word to.
Yeah.
There was one. Just a second. I'll put it on display.
Yes, we use the primary monocytes, and also we use the THP1's macrophages as a comparison.
Okay, great. So might be one more. Oh, okay, now if there are no urgent questions at the moment, I would.
Sorry, can I add some information?
Yes, please, sure.
As this protocol, the cultural protocols, including the co-culture protocols, were also published recently. So if you have any questions, or if you are interested in it, so please let me know. I can send also the links to you.
Thank you very much.
Thank you.
Very informative and very important to also promote these models, that more people get access to and start working with them to become more realistic in their models. And I'm very glad now that we have another presentation of a model which is in a different organ, the intestine model, why it is a challenge for in vitro research. So Angela, you're gonna let us know. Thank you for being here. So you still need to unmute yourself, your microphone. For unmuting, you find the button. It's a red button underneath the NanoSafe 20 sign.
All right, is that in the wrong part of the screen? But is the presentation still there? It's
yeah, now it's gone. Somebody removed it. Okay, please.
Okay, brilliant. Thank you very much for the opportunity to present something about an organ that is, well, usually a bit forgotten, let's say. So I'm very happy to be in this prominent liver-lung sandwich of patrols. The first couple of slides, I will focus on setting the scene a bit for the organ, for the intestine itself. Hopefully, it also becomes clear why it is such a challenge to mimic the organ for in vitro research. And then in the second part of the presentation, I will focus on the in vitro model that we are working with at the IUF, where I'm currently working as a postdoc. So just a couple of basic information, as I'm pretty sure that most of you have heard quite a bit about the intestine already. It is the largest part of the orogastrointestinal tract, and it's located mainly in the abdominal cavity of the human body. It is roughly divided into small and large intestine, and probably best known for its functions in food digestion and nutrient absorption, which is mainly taking place in the small intestine, as well as the regulation of the water household, which is mainly done in the large intestine. However, apart from this, it is also a very important contact and entrance organ for nanomaterials, as different types of nanomaterials can be, for instance, incorporated in food products or beverages. They can be part of pharmaceuticals, but also inhaled particles can be cleared from the airways and then swallowed afterwards, thereby getting in contact with the gastrointestinal tract again. However, I would really like to point out here that it's just a lot more than a weird tube that transports your food and magically absorbs nutrients, but it really is an organ of superlatives. It is forming one of the largest interfaces between the organism and the environment, the outside environment, which can be seen here in this cross-section that I've included as an example. So the three-dimensional structure of these folds and the microvilli that are formed on the enterocytes is resulting in a vast surface area. Therefore, it is also not surprising that it's one of the largest immune compartments of the human body, because this very critical balance of allowing nutrient absorption across the epithelial barrier while keeping out potentially harmful antigens needs to be guarded somehow. It also harbors the largest population of bacteria, the gut microbiota, and what is probably not so well known is that it contains a vast nervous system, the enteric nervous system. The gut is often called the second brain, and this is not so surprising anymore once you realize that it actually is the largest collection of neurons and glia outside of the brain. A couple of words to the structure and the anatomy of the small intestine. So, as said before, it is kind of just a long tube of several meters in length, And it is lined with a monolayer of epithelial cells, which fold into crypts and villi, increasing the surface area of the whole organ. The main cell types forming the epithelial barrier are enterocytes and goblet cells, which make up more than 90% of the cell types. The goblet cells are mainly known for the mucus production, which forms an additional very important physical barrier lining the whole epithelium. The intestinal mucus is also important for the gut homeostasis in itself and also provides an important living environment for the microbiota. Apart from the epithelial cells, we have representative cells or representation of the immune system. And here we have to distinguish between aggregated immune cells or immune compartments and isolated immune compartments. The Peyer's patches, to which also the famous microfold or M cells belong, can be counted to the aggregated immune compartments. And individual cells, as for instance, intestinal macrophages or also dendritic cells, are isolated immunocompetent cells. However, apart from this vast diversity of cell types, there is a lot more that needs to be considered when looking at the gastrointestinal tract, because you have an ever-changing environment depending on the kind of food you're taking in or whether you are actually in a fasted or in a fed state. There is a huge variety in the different digestive fluids, starting with the saliva, going to the gastric acid, in the stomach, and then the intestinal juices starting from the duodenum. For instance, encouraging a heavy change in the pHs depending on where you actually are in the gastrointestinal tract. You have the previously mentioned mucus and other digestive components like, for instance, enzymes. And then later on, going to the large intestine, a huge number of commensal bacteria, which can also influence the way that the intestine is reacting to, for instance, chemicals, pharmaceuticals, but also particles. So we have this multitude of individual factors which can be considered, but do not necessarily have to be considered in an intestinal in vitro model. The problem is that we actually still don't know yet which of these factors are essential to build a representative and a realistic model and which are just nice to have, or which may be important or may be essential for addressing very particular questions. The problem is that each of these factors, of course, increases the complexity of a model, and this can be both positive and negative. It can be positive in the sense that you increase complexity and thereby make your model more closely associated to an in vivo situation. But on the other hand, the complexity of a model is always inevitably related to the robustness of a model and its reproducibility. So the more complex you make a model, the more difficult it will be to set it up and obtain the same results in a different lab. If you have a look at the literature, there is really highly sophisticated in vitro models of the intestine out there, and the majority of them have been developed in the last 10 years. This includes, for instance, an involvement of a three-dimensional structure, the inclusion of flow, even the inclusion of microbiota, which I think until a couple of years ago, nobody would have expected to be possible. But you also see that there is actually very, very little application of this highly sophisticated model in applied research. So we still have to see where the development of intestinal in vitro models will take us in the future. So after having set the scene now, I would like to focus on a model that we are working with at the IUF, which has been developed, or actually advanced in patrols. I call this the macrophage model as opposite to the M-cell model, which was used by other partners within the project. To remind you a bit of what the major pillars of intestinal research are at the moment, we have kind of the gold standard, the use of human materials, for instance, generated from biopsies. But unfortunately, within patrols and at the IUF, we do not have the opportunities, the possibilities to really get to this kind of material. So we are focusing on the other two big pillars, the use of animal models on the one hand, but then also the further development and advancement of in vitro models. So as just mentioned, in patrols, we have focused on two different types of models. On the one hand, that is the so-called M-cell model. It was a triple culture setup of CACO2 cells, the E12 subtype of the HT29 MTX cell line, as well as Raji cells to induce an M-cell formation of the CACO cells. This has been done, Heriot Watt, as one of the partners in patrols, has focused on this type of model, but unfortunately nobody of them could actually make it today. So, but if you are interested in this, if you are interested in receiving more information on that, then please let me know and I can give you a contact to Heriot Watt. At the IOF, we have focused on the triple culture, also on the triple culture model of CACO2 cells and HT29 MTX cells, but we have focused on the introduction of an immunocompetent cell line, and here we have used THP1 cells as a model for macrophages. The important part about this model is that it can be used in both a healthy state, which I'm calling stable, or in an inflamed-like state. The macrophage model has been advanced in patrols from a previously described co-culture model of CACO2 and THP1 cells. This model has been described in detail in a publication a couple of years ago. And if you would like to know more about the seeding densities and why the parameters have been chosen the way that they are still actually used today in this triple culture model, then please check out the manuscript, because you will find a lot more information in there than I can give you now in this presentation. The predecessor model was now in patrols advanced by including the HT29 MTX cell line as a model cell line for goblet cells into the epithelial transwell layer. So therefore, we are here talking about a triple culture model of enterocytes, goblet cells, and a macrophage-like cell type. And when setting up this model can actually be divided in three individual stages. The first stage is focusing on the epithelial co-culture that is seeded onto transwell filters. Here, CACO2 and E12 cells are seeded in a 9:1 ratio and then maintained for 21 days in culture to allow for barrier formation as well as mucus secretion. What is happening over these 21 days, you can actually see in the graph to the right of the scheme. The barrier integrity is continuously increasing, which leads to an increase in barrier resistance, here measured as transepithelial electrical resistance. What we also see is that a very dense cell layer is formed where you can actually still identify the E12 cells within the majority of the enterocytes, within the majority of the CACO2 cells, which is these larger islands formed in the image to the right of the graph. The second part that we are waiting for is the release, the secretion of mucus, which we can detect either by specifically staining for particular mucins, as shown in the image at the bottom on the left for mucin 5AC, which is the major mucin secreted by the E12 cells, or more generally staining neutral and acidic mucus, as here shown by the PAS and Alchem blue staining. The second stage of the model development focuses on the THP1 cells. This is done 24 hours before the start of the co-culture. THP1 cells are treated with PMA for 24 hours. We are doing this in small culture flasks before they are then detached using Accutase and reseeded in transwell suitable 12 well plates. Why are we having to treat the cells with PMA? So one of the most obvious changes that is induced can be seen in the images to the right of the scheme. We have a change from a suspension cell line to an adherent cell type, which also is characterized by a very significant change in morphology. But which is a lot more important for us is what can be seen in the graphs below the scheme. It is the change in pro-inflammatory cytokine release that is induced by the PMA treatment. In the left graph, we see the cytokine release of interleukin-1 beta, interleukin-8, and TNF-alpha in response to lipopolysaccharides without PMA treatment, compared to the right after PMA treatment. And you can see here that especially the release of interleukin-1 beta and interleukin-8 is increased about 10-fold with the PMA treatment. And this is the amount, or we really need this high amount of pro-inflammatory cytokine release to be able to induce an inflammation-like state in the co-culture. The last stage of the model development is actually bringing these two first stages together. So the fully differentiated epithelial transwell cultures and the PMA-treated THP1 cells. Once you have the reseeded THP1 cells, you still have to decide whether you want to actually start the stable culture or whether you want to use the inflamed model. If you focus on just the stable or the healthy model, you can directly proceed by placing your epithelial transwell cultures onto your THP1 cells and you're done. If you want to use the inflamed model, the THP1 cells first have to be activated with a cocktail of lipopolysaccharides and interferon gamma, which has to take place for about 4 hours before the epithelial transwell cultures can be placed on top. Once you have the triple culture set up, you can maintain it for an extended amount of time. We have tried everything from just 24 hours up to 6 days without exposures and 5 days with exposures. This transwell setup, and especially the 12-well format, offers you the great opportunity to have a vast amount of different samples that you can probe. For instance, the supernatants from the apical and basolateral compartment can be collected separately or can be collected individually. And the transwell filter is actually large enough so that it allows you to cut it in half, use 1/2 of the cells for direct analysis, for instance, protein lysis or protein arrays, but also RNA analysis or DNA damage analysis with the COMET assay. And the other filter half can be fixed and used for stainings later on. There we go. Brilliant. I know this is a lot of graphs and I only want to go through them briefly because the first thing that we had a look at is, of course, the characterization of these two states and whether we are able to distinguish them without any doubt. So what I can say is that, yes, both of these models, or both of the states of this model, show very distinct features. Starting from this first graph here on the right of the text, we have the barrier integrity, which is temporarily reduced, impaired for the inflamed model, whereas for the stable model, it's all relatively, stable actually. Going further to the right, we have the LDH activity as an indicator for cytotoxicity. And we see that in the inflamed model, we have a continuous increase of LDH activity in the apical compartment, showing or suggesting that we have an ongoing cytotoxic effect of the strong inflammatory stimulus that is going on. At the bottom row, we have a very particular mucin profile, most notably a significant reduction in mucin 2 and mucin 5AC, as well as a very substantial increase in mucin 1. What is interesting about this mucin profile is that it's relatively comparable to the mucin profiles in patients with inflammatory bowel diseases, where you also see an incredible increase in mucin 1. These two graphs belong together, showing the cytokine release in the basolateral compartment of the stable triple cultures as well as the inflamed triple cultures. We have on the left side, the stable cultures, and we see that interleukin-8 is present, but at relatively low amounts. And for the inflamed model, there is a huge release of pro-inflammatory cytokines. These are only examples. We have looked at a lot more, and there's a vast array released by mainly the THP1 cells. Coming now briefly to application possibilities and later on also some limitations. What can the model be used for? We have so far used it for acute as well as repeated exposure studies, mainly using different types of nanomaterials. The model is stable for at least 144 hours, and even with repeated exposure studies, where we exposed the cultures for 5 days in a row, we managed to keep it working for at least 103 hours. We have also used a model for soluble compounds, for instance, diclofenac as a chemical control, but yeah, as said before, mainly sedimenting particles. The model can be used to study the effects in a healthy tissue, but also to have a look at whether ongoing inflammation is actually having an impact on tissue susceptibility. We have shown this with a predecessor model already and published it earlier this year, that ongoing inflammation actually enhances the toxicity of silver nanomaterials. And we hope, of course, to see a lot more of this happening in the future. Unfortunately, there is also some limitations, but I guess that holds true for most of the models. It is not suitable for low-density particles. That is actually self-explanatory because we are exposing in a submerged culture. So therefore, we rely on either substances that are soluble and therefore get in contact with the particles, with the cells, or high-density particles that actually sediment over a reasonable amount of time. If the particles are too low density and do not sediment, they will not get in contact with the cell layer, and therefore no effect is to be expected. Also, due to the lack of M cells, the particle transport is likely underestimated. So I would not recommend this model to actually, if you want to focus on particle uptake and particle translocation. It is also probably not capable, the model that is, to detect pro-inflammatory effects, which may sound a bit strange, keeping in mind that we have an immunocompetent cell type in it. But the problem is shown here in this graph at the bottom left. There is a very strong controlling effect of the epithelial cells over the THP1 pro-inflammatory response. What this graph shows is the release of interleukin-1 beta, interleukin-8, and TNF-alpha in response to LPS if THP1 cells were exposed in monocultures or, however, exposed in co-cultures. And what you see is that the release of all three cytokines is significantly reduced, but especially interleukin-1 beta and TNF-alpha are almost absent. And the problem is that these two cytokines are absolutely crucial to get the inflammatory response going. This controlling effect of the epithelial cells can partially be taken care of, can partially be reduced, but you need a really, really strong stressor. Here, for instance, we used EDTA to entirely disrupt the epithelial cell layer. And then there is an opportunity for apically added lipopolysaccharides and interferon gamma to sediment or to translocate to the basolateral compartment and activate the THP1 cells later on. However, this is also not always working because we have tried the same with diclofenac, which also destroys the cell barrier entirely, but there LPS and interferon gamma did not have any effect. So with this, I would like to thank the organizers for giving me the opportunity to present this to you, and also, of course, to Patrols for providing me with the funding to continue working on the in vitro models, and especially with a focus on the intestine, which hopefully will receive a bit more attention in the future.
Thank you very much, Angela, for your great presentation. I do try to find questions for you in the chat box, but so far I have not seen any. But it seems obviously that the more realistic such models become, a little bit less susceptible towards pro-inflammatory stimuli, as you were.
Yeah, absolutely. They become.
It could be. I mean, if one carries it a bit further to even including microbiota, and so could then become even more, or even less susceptible, so more robust. What would be your guess?
I think so too. So what we have seen recently, and it is an accepted publication, which hopefully soon becomes available in small, we have compared different in vitro models of the intestine, having, for instance, proliferating monocultures, then the epithelial co-cultures in themselves, and then the triple cultures together with the THP1 cells. And we have actually only seen effects of different types of particles, nanoparticles, in the proliferating monocultures. But already once you have an epithelial co-culture that has differentiated cells, that is a complete cell layer, let's say, a dense cell layer, then the reaction to at least very obvious or easy to detect endpoints is almost zero. So I think you would really have to go on very sensitive endpoints, like going onto the proteomics level or transcriptomics level to still see something there.
And the other point, which is also hitting the GI tract, is probably also the chronicity of such kind of things going on, not just up to 6 days, but even for longer times, isn't it?
Exactly. So in the beginning of patrols, we have discussed, or there was the idea to also expose the intestinal models for up to 14 days. We have decided against that because the turnover rate, the cellular turnover rate in the intestine is so high. So you actually have an average, a maximum lifespan of your typical enterocyte for 5 days. And therefore we have left it at 5 days for now. But of course, it might be important in the future to still extend that.
Okay, thanks a lot. There is also a question from the audience. I put it on display.
No, we have not, because primary small intestinal cells, at least to my knowledge, I'm not sure at the moment whether there is anything commercially available which has been treated one way or another, but using primary cells isolated from intestinal tissue is not as straightforward and not as easy to do as with other tissues. So you always rely either on the use of the mesenchyme or the introduction of it, or you really need to focus directly on the use of intestinal stem cells and develop intestinal stem cell organoids from that. And that is just too much effort for us. These protocols are too complex to do it on the side. You would have to fully focus on that and leave aside any other type of in vitro model for that. Yes, they are differentiated for 21 days.
Okay. Thanks for the questions. So definitely things can go on in the chat.
Yeah.
There was a little bit of delay, of course, with this online meeting, so maybe there came another one.
Do I still have time to answer that one?
Yeah, sure.
Okay, perfect.
I don't want to accelerate. I was just seeing no more questions.
Okay. Yes, we have. We are. This is one of our one of the research focuses actually that we are following. So we are, as a standard, always including an artificial digestion of the nanoparticles. For the last 1.5-2 years within patrols, we have actually always run a side-by-side analysis. So we compared whether this artificial digestion is changing the effect of that nanoparticles have in these intestinal models. And we are now actually focusing only on the on including nanomaterials after an artificial digestion.
Also very relevant point. Yes. Of course, we can always keep discussing in the chat. This is an advantage of online meetings. If there are no further questions now, we probably put it to some chat discussion between Angela and the other attendees. And I would then like to move to the next presenter, Samantha Llewellyn. And I will put on her presentation. Actually, she provided a film again. And then she will, of course, be available for any further question.
So welcome, my name is Samantha Llewellyn, and I'm going to be talking to you today about advanced engineered nanomaterial exposure regimes for more realistic dosing scenarios on 3D liver models in vitro. So as a bit of an overview, the liver is the main detoxification centre of the human body and is one of the only organs that possess the capability to regenerate. In addition to this, it is the main site of secondary nanomaterial deposition following either primary routes of exposure, so ingestion, inhalation, injection, and dermal penetration. The liver itself contains of two main lobes, both of which have 8 segments that embody thousands of liver lobules. These lobules, as shown in B, are hexagonal structures constructed by repeating segments radiating out from the central vein. So each segment, as shown here, links to one another by the liver sinusoids and consists of the portal triad, so the bile duct, portal vein, and hepatic arteriole. Within the liver, there are two main cell populations, parenchymal and non-parenchymal cells. Approximately 80% of the liver volume is occupied by the parenchymal hepatocytes, whilst the remaining non-parenchymal fraction is made up of endothelial cells, stellate cells, and the resident liver macrophages, Kupffer cells. These cells work together to maintain metabolic homeostasis and detoxify any xenobiotics. So based on this and the principle that 2D cultures do not encapsulate the intricate multicellular interactions and metabolic activity observed in vivo, as well as their 3D counterparts, we began to develop a 3D cell line-based liver model. So the aim of this work was to advance existing 3D in vitro liver models to enhance their physiological relevance and develop a liver model able to retain both its proliferative capabilities whilst remaining viable for 14 days in culture. So this was to allow for long-term and repeated nanomaterial exposure regimes to be evaluated, but also with more of a primary toxicological focus on genotoxicity endpoints. So our model itself, as depicted here, is established using the hanging drop method to form 3D liver spheroids, which consist of about 4,000 HepG2 cells per spheroid. This equates normally to about 500 micrometers squared in diameter, and they are available for over 10 days in culture. So in preparation to build this model, there are a few key components you'll need to bear in mind. This model is based on the HepG2 cell line from ATCC, and if you're looking to do a genotoxicity-based study within this model, I advise that you run a preliminary experiment on the cell line first to assess the background genotox prior to then diving into your research, as some supplier stocks do have a higher background than others. So in addition to this, and believe it or not, the 96-well plate you use is important, as the lids on some of the plates can be looser than others, which makes it more difficult to form full plates of spherical shaped spheroids. And then most of the reagents will be prepared on the day of, but the 1.5% sterile agarose gel will need to be prepared in advance. On the right, we've got a little bit of a kind of overview of the breakdown that will to be expected and what will need to be done on particular days. And this entire process can take anywhere between 10 days to 2 weeks, depending on your nanomaterial exposure length. So once we developed this model, we did some baseline characterization work to see how the model performs and compares to other models on the market. So we found this model remained viable for over 10 days in culture and was shown to maintain, if not increase, albumin and urea production throughout the 14 days in culture. This highlights that the model remains functional throughout the period. So as most spheroid models, the development of the necrotic core often limits the longevity of these proliferating models, as the larger and more compact the spheroid becomes, the harder it is for the oxygen and nutrients to diffuse through. Some models, like the primary human hepatocyte models, offer a longer culture period as they are smaller, but limit the evaluation of fixed DNA damage as they are non-dividing static models. So it does completely depend on the specific toxicity endpoints you wish to study. However, I shall take this opportunity to take you through the development of the 3D liver model that we have developed and its particular applications. The methodology I'll be explaining or showing to you has also been published in Jove, and there is a video coming soon to support that. And in addition to this, we do have a co-culture model available, but this characterization data is yet to be published. Okay, so the process begins with seeding the 3D liver spheroids, and in short, we seed 20 microliter drops of HepG2 cell suspension onto the lids of the 96-well plates. I have prepared a little video to help visualize this process. I'm not sure how well this will come across online, but we'll give it a go and I'll talk you through it a little bit. So initially, we add PBS to the base of the plates to ensure, or to maintain hydration and ensure that the spheroids do not dry out during the 3-day formation process. So you need 100 microliters of PBS, which will be added to the base of the plate. So once this is completed, you'll take a cell suspension of about 2 × 10⁵ cells per mil. This will equate to about 4,000 cells per spheroid in each 20 microliter drop that gets added to the surface of the lid. So when adding these drops, take care to make sure the spheroid droplets are actually added in the center of the grooves, as you can see there. As this will make sure that the spheroids form directly in the center of the drops. For each plate, about 5 ml of cell suspension is required in order to seed the full 96 wells. Once you have seeded these, you then flip the lid and place back onto the bottom of the 96 well plate. This can be quite tricky and does require a lot of practice, because sometimes whether you go too quickly or too slowly, it can affect how the spheroids then stay on the lid of the plate. Okay, so what to expect? In most cases, not all 96 spheroids seeded will make it to the day of exposure. Some are lost during either the lid flipping stages, or others during transport to and from the incubator, or even whilst forming over the 3 days in the incubator. A common cause of the misshaped spheroids can be just from the disturbance of going in and out of the incubators aggressively, but it might be worth putting a note on the outside of the incubator just to inform other colleagues that may also be using that incubator. So as shown here between D and F, and then highlighted with a green outline, is a good quality spheroid, so it's what you'd expect to see. So you want a compact, singular, spherical structure that hopefully is formed over the 3 days in the hanging drop. Or you could have poorly formed spheroids, as shown in G to I and highlighted in the pink, where you've got protrusions and it's kind of maybe a little bit stuck to the bottom of the well, or you've got bits of cells that have broken away from it, or even individual kind of independent spheroids that have also grown within the well itself. So ideally, if this happens, we don't tend to use those spheroids. So yes, you kind of want them to look very similar to kind of D and F really before you proceed. Following the 3 days in culture, we transfer the hanging drops to the base of the 96 well plate, pre-coated with the 1.5% agarose gel, as shown in the following video. So to do this, you carefully remove the lids and you then empty the PBS out of the base of the plates. I tend to use just a bucket to empty all the PBS out, and then tap any of the remaining liquid out using just some glue roll. You then microwave the agarose gel to make sure it's molten, and use about 50 microliters of the gel to the bottom of the 96 well plate. I normally leave it for a couple of minutes before adding any media to the top of this, as you need the gel to set first. So once set, you can add 100 microliters of media to the plate, and then we just replace the lid back on top. You then take the 96 well plates and put them in a plate centrifuge, spinning them for 3 minutes at 1000 RPM. And these should then cause the Hep-G2 spheroids to drop from the lid of the plate to the base of the wells, as shown here. You can see the little individual spherical dots in the center of the wells. So after this, we allow the spheroids to settle for 24 hours before we expose them to varying concentrations of engineered nanomaterials. Prior to the exposure, these materials are pre-wetted in 95% ethanol and sonicated continuously for 16 minutes in 0.05% BSA at 21 amps, as described in the NanoReg dispersion protocol. So all the materials we have used have been provided by the JRC, with the exception of silver, which is from Sigma. Our aim was to assess the toxicological effects of low-dose, longer-term ENO exposures, And so the concentration range that we generally work with is 0.2 micrograms per mil to 10 micrograms per mil. It is important to note, however, that these doses are prepared as a double concentrate to account for the 50% dilution when adding 50 microliters of the dose medium to the 96-well plate, which already has 50 microliters of culture medium in there. So I always make up my doses double concentrated. So following the exposure period, the supernatant and steroids can be harvested simultaneously or independently if necessary. So for supernatant harvest, about 50 microliters of the supernatant is taken from the surface of the wells in order not to disturb the cells, whilst the full 100 microliters should be taken, steroid included, if harvesting both simultaneously. So this 3D model is compatible with a number of biochemical endpoints as listed here, so from cytotoxicity and liver functionality to inflammatory markers and genotoxicity. Each plate can yield about 5 mils of supernatant, and so any of the assays based on supernatant, such as your liver function or inflammatory-based ELISA markers, one 96-well plate will be more than sufficient. However, for cell-based assays, more plates may be required per dose, depending on how many cells the assay requires. So one key feature of this model, though, is it is able to support fixed DNA damage assessment using the micronucleus assay, as it does remain proliferating throughout 14 days in culture. So this is just a few applications of this liver model. I would have gone into a bit more data and maybe shown you some of the results, but as this is more of a teaching module, I'll just show you some of the kind of applications that we've used this model for. A little bit of what does the liver see? So with the liver being a secondary site of exposure for engineered nanomaterials, following systemic translocation from the primary exposure routes mentioned earlier, it is highly unlikely that the liver will be exposed to pristine nanomaterials, as interaction with a variety of molecules in these different cellular compartments can transform the physicochemical properties, so surface chemistry, protein corona, morphology, dissolution of these materials, which can then affect their biological interaction and the toxicological output. So to mimic this potential biotransformation, we developed an SOP whereby the nanomaterials undergo a series of incubations in synthetic biological fluids that was aimed to then simulate the ingestion and digestion of nanomaterials specifically. So initially, the ENMs are incubated at 37 degrees for 30 minutes in a gastric, so pH 2.7, simulant fluid, followed by 30 minutes in an intestinal fluid at pH 9.5. This is a protocol devised by Angela Kämpfer and her colleagues at the IUF in Germany. Following this, we then decided to add an additional incubation of 1 hour in human blood plasma prior to further dilution in media and exposure to the 3D liver cells. So this particular SOP or scenario mimics the gastrointestinal tract kind of ingestion exposure scenario to the liver. So furthermore, we had a look at the manner in which the ENMs are dosed onto the cells within in vitro cultures, as this may influence their biological interaction, as humans are usually exposed to low doses of ENMs over extended periods of time, as opposed to a single high dose as typically applied in cell culture practice. So with this in mind, we decided to address this by undertaking a fractionated repeated dosing regime, as well as a bolus single hit dosing regime for a longer term 120-hour nanomaterial exposure. So for the repeated dosing regime, the final concentration is fractionated into 5 equal concentrations and dosed daily, which will inevitably amount to the same single bolus dose applied on day 1 in the other regime. This is kind of depicted in the diagram here, where you can see the 5 micrograms per mil final concentration has been split into 5 1 microgram per mil doses over the duration of the 5 days. So on the day of harvest, we'll then look at the same toxicological endpoints, so the micronucleus assay, inflammatory markers using the ELISAs, and just general liver functionality as well, just to assess if this has made any difference in the way that you dose the nanomaterials. So to conclude, although with its limitations, this advanced 3D in vitro liver model is able to support a range of toxicological endpoints for nanomaterial screening. We've been able to develop an SOP for more physiologically relevant nanomaterial dosing regimes with a tiered kind of testing strategy to assess whether the E&M biotransformation really has an effect on the toxicity kind of outcome. In addition, we actually found that there was little to no difference in fixed DNA damage observed between repeated and bolus long-term exposure regimes. Now, we're currently doing a little bit further investigations, to say, with the pro-inflammatory markers and liver functionality, but at this stage there doesn't seem to be much difference between whether you do a bolus or a fractionated dosing regime. But yes, I'm sure more information of this will be published in due course. So if you'd like to find out anything more about the project, the links to our website and social media platforms are listed here. Otherwise, I thank you all for listening, and I hope that you found that useful in some way, and I am happy to take any questions.
Well, there are questions, Samantha. Please unmute your microphone so you can answer. The unmute function is underneath the NanoSafe 20 sign. So please press the middle button of the three ones which you might see. This is looking like a microphone, so you can unmute yourself. So we got a couple of questions for you, Samantha. I'm quickly showing my screen. So here in this sign, you have the unmute, and I would ask you to unmute your microphone so you can answer the questions. Let's have another trial. I did quickly make you attendee and presenter once again and unmuted your microphone, unlocked your microphone. So maybe now it functions. This is unfortunate. So we will come back to the questions maybe later on. I would ask you, Samantha, to stay with us and refer to the questions later on. Meanwhile, we give the floor to Marije Niemeijer to start with her presentation.
Yeah, thank you. I will set up my screen sharing.
Please, be so kind. Samantha, maybe you quickly sign off and sign in again, and then maybe it functions, because we would be really glad to kind of deal with these questions for you.
So can you see my screen?
No.
Okay.
But we saw it shortly, wasn't it?
No, still not?
No, you need to go to screen sharing, which
Yeah.
is the fourth button from the top, so without the menu button itself.
And now you see it?
No.
Okay, that's weird. Let's see. Okay, let's try again.
This is actually what we're waiting for. Another trial. Okay.
Now you
Now
see
we see your screen. We see your screen now, and if you go now to your presentation, then we might be able to see your presentation. Okay.
You see it?
We are making progress. Yes, looks good.
And now I'm trying to make it big because you don't see it, right?
Presentation mode. Looks good. Okay.
And now it's big?
Yes, it's fine.
Okay. Great. Thanks. So yeah, thank you for giving me the opportunity to present here in this session. So my name is Marije Niemeijer from Leiden University, and I'm also working within the patrols. So today I will present a 3D Hep2 stress response reporter, which is imaging based to enable nanoparticle toxicity screening. So when a chemical or nanoparticle enters the liver and reaches the hepatocyte, it provokes a certain molecular initiation event. And this may lead to the accumulation of certain types of stress inside these hepatocytes, such as endoplasmic reticulum stress response, DNA damage signaling, or the oxidative stress. And a cell tries to cope with these different kind of stresses to activate specific adaptive stress response pathways, such as the unfolded protein response, oxidative stress response, or the p53-mediated DNA damage signaling. And this to try to restore homeostasis during stress conditions by these nanoparticles inside the cell. However, when the stress is too severe, a certain breaking point will be reached and the cell switches to apoptotic signaling, which may in the end lead to either necrosis, apoptosis, and leading to certain adverse events inside the liver. So to be able to have a prediction of the development of these adverse events in the liver, it is of value to map the activation of these adaptive stress responses to allow mapping of different kind of stresses provoked by these nanoparticles at an early stage during development to this toxicity and adverse events. So yeah, a cell has different adaptive stress responses to cope with these different types of stresses. And they are regulated by a certain sensor, which controls a specific activity of transcription factors of these four different stress responses, which leads to the activation of certain downstream target genes, enabling the cell to remove this type of stress in the cell and to restore homeostasis. So if you can map the activation of these different pathways by looking at these specific genes at different levels within these pathways, we can have more insight of how these nanoparticles induce stress inside these hepatocytes. So to be able to follow this activation of these genes of these different adaptive stress responses, at Leiden we developed an Hep2 reporter platform by using the Bach recombinering technique. So here on the left you see the Hep2 cell being transfected with certain plasmids containing the gene of interest with the GFP tag. And they're being transfected and selected so that we end up with cells that specifically express genes that are connected to a GFP tag. So then when a certain stress is inside the cells, we see activation and induction of this GFP fluorophore. And this we can do for all different kind of stress responses, such as oxidative stress, the UPR, or inflammation signaling, DNA damage signaling, or other types of stresses, to build up this reporter panel to follow different types of stress upon nanoparticle exposure. So here's an example how this may look like. So you have your Hep2 cells, and they're exposed to a certain chemical or nanoparticle, and then over time you can follow the induction of this GFP reporter connected to a certain key gene within these adaptive stress responses over time, and this indicates that there's a certain type of stress inside these cells. And this GFP signal you can then quantify. So here you have your image with the nuclei in blue with the GFP. You can first quantify the single cells using specific software, such as Cell Profiler. So you can define single cells based on the Hughes signal and also the complete cells. So then you can also measure the GFP intensity within the nuclei, but also within the cytoplasm of each single cell. And this you can further analyze to see, okay, which kind of nanoparticles or chemicals induce which type of stress responses at a certain concentration. So for instance, if we zoom into one of these stress response pathways, such as the oxidative stress pathway, normally NRF2 is being kept inactive by the sensor KEAP1 and is being ubiquitinated and degraded by the proteasome and is then in an inactive state when there's no oxidative stress. But when there is oxidative stress, such as by this known compound or a nanoparticle, then NRF2 is able to move away from the KEAP1 sensor and can accumulate inside the nuclei and then activates its downstream target genes, such as sulfurdoxin-1, to eliminate the oxidative stress. So here you see an example of these different reporters for each level. So we have a reporter for KEAP1, the sensor, NRF2, the transcription factor of this pathway, and sulfurdoxin-1, which is a downstream target. And you can see that we can then follow the activation of these genes over time when they're exposed to a known oxidative stress inducer. You see a clear upregulation of this GFP signal. And this you can then quantify and follow the dynamics, activation dynamics over time. So here on the x-axis you see the time versus the GFP intensity, which is quantified. You see that there's a time-dependent induction and that also the different genes within the pathway have different time dynamics. So NRF2 is activated really early, followed by the activation of sulfurdoxin and also being concentration dependent. So in this way you can follow a whole pathway upon chemical or nanoparticle exposure. So a typical chemical or nanoparticle screening setup is first seeding the Hep2 reported cell lines which are interested in a 384 well format, and then perform Hughes staining to visualize the nuclei, followed by drug exposure or nanoparticle exposure, and then do confocal microscopy to follow the activation over time. So we can do live cell imaging, where the cells, the plates are kept at 37 degrees, and we can image each single well every hour for instance, 24 hours or even up to 72 hours in this 2D setup. So with this data, you can extract different features. So you can extract different time responses, but also concentration-dependent response. And based on this, you can define, for instance, the point of departure, so the concentration at which we start seeing an induction of a certain stress response pathway, but also the EC50 or the slope or the maximum induction of this GFP response. And we can do this at the single cell level. But for nanoparticles, it's essential to also test them for long-term repeated exposure scenarios. So we wanted to go from 2D to 3D for this by using a spheroid system for the Hep2 cells. So here we also use 384 well plates and add 11 microliters of Matrigel, which is still in a liquid phase, so kept at 4 degrees, so that you're able to pipette the Matrigel in each well. And then these plates, which contain only Matrigel in each well, are then incubated for exactly 43 minutes at 37 degrees in the incubator. And this allows to solidify the Matrigel for somewhat. And then after this 43 minutes, 1,000 cells per well are added, which was contained in 50 microliters of medium. And this allows to that these 1,000 cells sink into the Matrigel layer. But because they are already 43 minutes incubated at 37 degrees, they will sink into the middle of the Matrigel, so not directly to the bottom, but also not on top. So with this 43 minutes, they will end up approximately in the middle of the Matrigel layer. And then after plating, the medium is being refreshed for 3 to 4 days, for at least 21 days. And this enables to let them form spheroids within this Matrigel layer. So this is how it looks like. So first on day 1, they're still single cells. So that's essential that they are single cells, because if you have already some clumps in, then they will form bigger spheroids in the end. So it's essential to have single cells to remain consistent in the spheroid size later on. And then after 21 days, you can see that they form nice spheroids within each well. And these spheroids are stable for at least 14 days, so this enables repeated exposure scenarios with nanoparticles. So we also looked at the proliferation of these Hep2 spheroids. So normally in 2-day, Hep2 cells are highly proliferative, but when they are cultured in this Matrigel layer, they stop proliferating after 14 days. Which is shown by the Ki67 staining, also seen on the right here with the IF staining. And we also looked at the differentiation status of this 3D Hep2 spheroids. We could see that they show an increased expression of albumin and also secretion of albumin, indicating that they have an enhanced differentiation state compared to its 2D state of these Hep2 cells. So we can also use this setup, so this 3D setup, in combination with this GFP reporter system to follow the different stress response pathways also in this 3D setup. So we can look at, for instance, oxidative stress using the sulfur-redoxin reporter. So upon chemical exposure, in this case, you can see a clear induction of this reporter upon exposure. But we can also do this for endoplasmic reticulum stress with 2 different reporters, but also for DNA damage signaling, where you can also see a significant increase in the GFP signal upon exposure to known stressors. So what would be the typical setup for screening of nanoparticles using this 3D setup with these Hep2 GFP reporters? So on day 0, we can seed these specific reporter cell lines in this Matrigel layer, and then refresh 2 times a week for 3 weeks to allow for spheroid formation, so they become like this in the photo on the bottom. And then we can do a nanoparticle exposure for up until 14 days repeatedly. So on day 0, we remove then the medium that's on top of the Matrigel, and then add fresh 25 microliters of medium, and then add on top 25 microliters of 2 times concentrated nanoparticle solution. And this we can do every day up until 14 days. And in the last day, we add also Hoeg staining to visualize the nuclei within the spheroids. And then after a certain amount of exposure time, we can do also, again, imaging of these 3D spheroids using confocal microscope. And then we make different Z stacks at different heights within the matrigel layer to visualize the complete spheroids at different heights. So we use here steps of 30 micrometers, also being visualized here above on the right. So then you have all these images on the different Z stacks, and then we will make a 2D projection based on the maximum pixel intensity of these different Z stacks, so that you have actually then a 2D projection of the different heights that you have imaged within each bell. And this you can then segment based on the Hughes staining using the NIS elements analysis software, and then quantify the GFP intensity within these segmented spheroids. So this is how it looks like when you would expose certain nanoparticles within these spheroids. So for instance, we have tested reporters for the UPR, DNA damage and oxidative stress. And you can see that after 14 days of repeated exposure, that we see an enhanced signal of these various reporters, so that you can visualize, okay, which stress responses are being activated upon exposure to these nanoparticles. And this you can then quantify and visualize within overview graphs, so you can see that there's a dose-dependent induction of these stress response reporters for the different nanoparticles, and that it's also time-dependent. So here on the x-axis you see the different concentrations, and on the y-axis the GFP intensity that has been quantified for the 4 different reporters in this case. And you see that the 4-day repeated, so in the dark blue, you can see that at lower concentrations the reporters are already being activated, while the 5-day repeated exposure scenario, you see that only at the highest 2 concentrations we see an activation of these reporters. So with this reporter panel, both in 2D and 3D, we can do high throughput mechanism-based toxicity screening, and it enables both single and long-term repeated exposure screening in 2D and 3D setting. So as a next step, we also want to test these reporters in the hanging drop method that Sam just presented, and that we can also compare this with each other with the different setups. So hereby I would like to thank my colleagues at Leiden University, but also collaborators also in Patrols, and also for your attention. And I'm happy to answer any questions.
Thank you, Marije. There is already one on the screen of the platform. I put it through and display for you.
Let's see.
To exit the screen.
Yeah, that's indeed a good question. So yeah, we have tested up until 100 micrograms per milliliter, and there we saw indeed with the highest concentrations that there's so much saturation of this nanomaterials that it will interfere with your GFP signal. But it was primarily for the highest concentration that we tested. Yeah, I see another question in the chat, like about how to quantify the amount of particles within the spheroid. So that's a good question, and we are currently testing it with electron microscopy to quantify and see, okay, also where the nanoparticles end up, if only the outer cells take up these nanoparticles, and how the distribution is within these spheroids, especially since it's embedded in matrigel. So matrigel might interfere with the take-up of these nanoparticles. But still, also visually, we see that a lot of nanoparticles also end up on the bottom. So yeah, there is nanoparticles going through, but we still need to quantify this further. Yeah, so currently these nanoparticles that I've been testing are not tagged. So that would also be a solution to also test nanoparticles that are tagged to see what is the distribution of these nanoparticles within the spheroids. But it might maybe differ somehow a bit to the nanoparticles that we have been testing. But still, it would give a good indication of how the distribution is of these nanoparticles. Yeah, I see a question about the responses to nanomaterial exposures, but I can also definitely share the slide with you, Trine. Yeah, so within patrols we have also work packages that focus on in vivo comparisons. So we are also planning to integrate to do the in vitro in vivo comparison to see how it matches with each other indeed. Yeah, that's also why it's relevant to have the internal exposure of these nanoparticles to also compare it.
How about availability of such reporter cell lines to other laboratories you provide them?
Yeah, so recently it's being commercialized with a company named Toxis in the Netherlands. So yeah, just recently they fused with another company, Toxis.
And are you planning to extend to further genes of interest in the reporter lines, or?
Yeah, so also based on transcriptomics data, because the initial reporter panel was based on literature, but now we are also selecting genes that are being co-regulated based on TG Gates data set. So that's a chemical-based transcriptomics data set to see which genes are now most relevant in liver systems such as the prime human PET cells and HepC2 cells, and then compare to in vivo and which are being which are relevant in vitro and in vivo situation.
Okay.
But it's still ongoing.
Yeah. Thank you very much. We have still one more workshop today. We take something like 5 minutes break. I would say that we reconvene at 5 minutes before the hour of 5 o'clock CET, so Central European time, to give ourselves a little bit a chance to get some fresh air into the head, open the windows, straighten the legs, being ready for the next session by Trine Berthing from the Danish Research Institute for Workplace Safety, Workplace Environment, also on advanced cell cultures and bioimaging techniques. So I will leave the room open, of course, and just upload the next couple of presentations and films. You can, of course, continue chatting in the chat room, and then we are going to listen to Trine at 5 minutes to 5 o'clock. So just 5 minutes behind schedule. So, welcome back. 5 minutes to 5 o'clock, Central European time, of course. We have one more presentation. We're staying in the area of advanced cell culture systems, and we are now getting an insight provided by Trine Berthing from the Danish National Center for Workplace Environment on a very costly technique, which became available a couple of years ago, Cyto-Viva Darkfield microscopy for localization of particles in vitro and in vivo. So Trine has been carrying this to quite extensive experimentations. And she prefers to show us her presentation also with a recorded MP4 of her presentation. Of course, it's available for questions, and then she also gives us a video with a lab but a lab demo. Good. And I guess during this presentation, she's gonna introduce also her place and herself.
Hi, and thank you for joining the last training session of the day. My name is Trine Berthing, and I'm a microscopy specialist at the National Research Center for the Working Environment in Denmark. And the training session will be about enhanced dark field microscopy for localization of particles in vivo and in vitro. The agenda for the next 30 minutes is that I will give you a short introduction, and then I'll give you show you a demonstration video of the microscope from our lab. Then I will show you some application examples of this technique, and in the end you can ask me questions. At the National Research Center for the Working Environment, we have for many years now had a vision within nanosafety, which is to ensure the safe use of nanomaterials in Denmark. And for that we use in vitro and in vivo toxicology. We are also involved in the EU project Patrols, and the aim of Patrols is to develop in vitro and in silico tools for nanosafety. Fate of nanomaterials in an organism is one of the key aspects of nanotoxicology. For example, if you inhale nanoparticles, a small fraction can go into systemic circulation in the blood, and then there's a risk that the particles will accumulate in secondary organs, for example, such as the liver. And there are several ways to look at the fate of nanomaterials, and one of them is to image particles in tissues with cellular resolution. A few technical details on the setup. It is called Cyto-Viva Enhanced Darkfield and Hyperspectral Imaging, and it is label free. The particles are detected simply by the light they scatter. The detection limit is about 15 nanometers, and it's called enhanced dark field because it improves the dark field signal a lot. It's actually developed to detect, specifically to detect the nanoparticles. Here is standard dark field, and over here is enhanced dark field. With the hyperspectral setup, you can record the reflectance spectra from the particles from 400 to 1000 nanometers with a very high spectral resolution, and this is why it's called hyperspectral imaging. Here you can see the type of images that comes from the microscope. So first, here on the left you have a standard bright field image of a tissue, and you can see that the background is bright. Now the same tissue imaged in dark field, you have sort of an inverted contrast with a dark background. And common for these two types of imaging modes is that in the pixels you have information on the red, green, and blue intensity levels. But then when you take this same sample and do a hyperspectral image, then the information you gain is that for each pixel, you will have the reflectance spectrum from 400 to 1000 nanometers. And I think I'll just jump right into the demonstration in the lab. So have fun. This is our setup where we have, starting with the light source over here, quartz halogen lamp. The light goes through the light guide into the Süße-Weber condenser, Darkfield condenser. It goes through your sample, and only the light that is scattered from the sample is then goes through the objectives and either recorded up here with the camera as an enhanced Darkfield image, or you can shift the light path here to go to the back where the spectral camera is to record a hyperspectral image. Add a few drops of immersion oil to cover the lens completely. Now you're ready to mount your sample, and the sample should be thin enough to allow light to transmit through the sample. And then you slowly raise the condenser until the oil touches the sample. And then you're ready for imaging. Next step is to adjust the height of the condenser so that the light is focused in the smallest possible circle in the middle of your sample. Then you can change to a higher magnification and start scanning for particles. And most particles, if they scatter light, they will appear white in a dark field image. So you can start at this low magnification and look for any bright spots. And what we're looking at here is a mouse liver. The black in the middle is a vein, and the small yellow circles are red blood cells. All the red circles around are the nuclei of the liver cells. To get a closer look at the objects that you found, you can change to the highest possible magnification on your setup. For us, it's 100x objective. And now you see maybe more clearly like the donut shape of the red blood cells, and you can adjust the focus for one of these scattering agglomerates. And then also you need to adjust the exposure time. Usually, if it's like here, it's metal oxides, the scattering intensity of the particles is so high that you need to lower the exposure quite a lot to be able to see the actual particle agglomerate. Next, I would like to show you some of the most common artifacts that you can find especially in histological tissue samples. It's actually this small white spot that you see in the middle, which is very common and which actually looks a lot like nanoparticles in tissue also would look like. And these bright spots, you can find them either in good samples, there are very few, and in other samples you will have a lot of them there. So you need to be very careful and know your negative controls. Finally, I will show you how to record a hyperspectral image. I'll just change to a different software called Envy. And here you can choose to either record the spectrum of the full image or just half the image, as I've chosen here, so that it won't take too much time. Now it starts scanning the field of view line by line and recording the spectra for each pixel. So I speeded it up. Here's the particle agglomerate. And now it has finished the scan. And you can see here, this is then the hyperspectral image. So it looks like a copy of the enhanced Darkfield image. I'll bring out a zoom for you here of the agglomerate. But the data that the hyperspectral image contains is that you can right-click on any pixel in the image. Like this. And then you get the reflectance spectra going from 400 nanometers to 1000 nanometers. And you can click around here on the agglomerate to see all the different spectra that it has recorded. Let me just collect a few spectra so that you can compare. This is two spectra from the agglomerate. And I'll try and get a spectrum also from this nuclei that is close by. It's probably a Kupfer cell nuclei from a Kupfer cell that has taken up this the metal oxide nanomaterial. And you can see this green curve that showed up, that the intensity is a lot lower than the scattering particles. I click here also on the cytosol of a hepatocyte. That's the blue curve that came in the bottom. And that is actually all I wanted to show you today. Let's look at some application examples. This first example is actually the same as I used in the demo just before. So it's cerium dioxide in mouse liver, but I wanted to show you also the corresponding bright field images. So here, this is what you saw in the demo, and this is the corresponding bright field image. And this is to give you the impression that in bright field, you would probably never find these material agglomerates, whereas they come up nicely in enhanced dark field. Also, if you see in this high magnification bright field, then you can actually see the particle agglomerate. And also, if you're experienced in histology, you can, based on these standard hematoxylin and eosin stain, you can identify which cell types are interacting with your nanomaterial. Next example is titanium dioxide, so another metal oxide. This is now in lung tissue. So you see all in the bright field image, you see all the white is all the alveoli and the airways. And again, you see very clearly where you have the titanium dioxide, and at higher magnification, we can see that this is a macrophage who has phagocytized a lot of titanium dioxide, and here you have the titanium dioxide in the epithelium of the lung. This example is from a study where mice were exposed to multi-wall copper nanotubes, Mitsui 7. And then 1 year later, we actually thought that all the copper nanotubes had been cleared from the lungs because we couldn't see any in bright field. But when we then took the samples to enhanced dark field microscope, we found that actually there were single carbon nanotubes hiding in the lung tissue, spread all over the lung. This is an example where the enhanced dark field does not give you any advantage. So this is lungs with carbon black. The carbon black is black in bright field, as you see here with the arrows. And it's also black in dark field. And this is because the carbon absorbs the light rather than scatters the light. Here in this higher magnification, it's a macrophage in the lung. And this is two large aggregates of carbon black, which you basically don't get any signal from it. And this is actually the same for most carbon-based nanomaterials, also, for example, graphene, and most of the carbon nanotubes, which give a really low dark field signal. Final example is from an in vitro model which has been developed for use with nanomaterials in petrols. This is small spheroids made from primary human liver cells. And in petrols, these small spheroids has been exposed for 3 weeks to titanium dioxide and cerium dioxide. And in the study, we were curious if we exposed these spheres to nanomaterials, if they would simply only touch the outer surface of these spheres. But then when we made thin sections and imaged with enhanced dark field, you can see here that the spheres, the liver spheroids, they nicely take up the nanomaterial, so that also the cells deep in the spheroids are interacting with the nanomaterial. Yeah, I had the idea I wanted to make a library of artifacts, because there can be really many artifacts that you discover when you go to enhanced dark field microscope. Because any dust or any bubble will scatter light. This is the example that I showed you also in the demo. It's the most common type of artifact. It's these spotted artifacts, which can be different colors. Here you have blue, white, yellow, and it's most probably a formalin heme pigment. So it's an artifact caused from the formalin fixation. Here you have a placenta full of white scattering stuff, which is has not been in contact with any particles, so it's not. This is lung tissue. Here you have the alveoli. Also, again, full of highly scattering objects, which to begin with I thought was nanoparticles, but until I looked into the control samples. And this is most probably because of poor cryopreservation. I also wanted to just note that also blood actually scatters quite a lot of light. So for example, in the spleen, where you have a whole lot of blood and hemosiderin, you can have a lot of scattering background, which makes it a bit more difficult to find nanoparticles. So the best advice to avoid artifacts is to have proper and clean histological tissue processing. Definitely avoid dust and bubbles. And most importantly, you need to scan first some control samples to really get to know the common artifacts. Okay, so the take-home message for me is that I hope I gave you the impression that the CITUVIVA Enhanced Darkfield is simple to operate, but also easy to misinterpret. And I showed you that it is really good for detecting metals and metal oxides, for thick multi-wall carbon nanotubes such as Mitsui. It's also really good. Most carbon-based materials, unfortunately, does not scatter so much light. And also, I hope I also touched upon that imaging the localization of these particles in tissue can support your in vivo, in vitro toxicology studies. And if you would like more information, you are welcome to write me an email. You can also go to CITUVIVA's homepage. They also have some video tutorials there. And I put 2 of my favorite publications on the technique, where they cover advanced use of spectral mapping and also correlate the technique to other types of assessments of biodistribution. And finally, a great thanks, of course, to my colleagues at the National Research Center for the Working Environment and for our partners in patrols. The data I showed today was funded by the Danish government and also European Union's Horizon 2020 program.
Thanks a lot, Trine.
I really hope that you have a lot of questions for me. Thank you.
Thanks a lot, Trine. Yes, indeed, there were really questions accumulating already in the chat box, and I put them through on the main screen that you can discuss them. So please be so kind and switch on microphone and camera that we can discuss it. Obviously, quite attractive for many people. This topic.
All right, I hope you can hear me. So Shireen is asking if there's any limitation to the particle types. Yes, there definitely is. So of course, plasmonic particles are the very best. Metals, metal oxides, really good. As I showed, many of these carbon-based nanomaterials often is quite difficult because they absorb light rather than scatter. Will this technique work for? Yeah.
Yeah, this is what.
Thanks. Yeah. And so also, of course, it needs to be particles. If they're so soluble that they're just dissolved, then you won't see anything in dark field either, even though if you have the chemical elements there. I tried this with the zinc oxide, for example. I couldn't see any particles. If I have more than one type of nanoparticles, can I differentiate them? No. So, well, for example, titania and ceria, I cannot. They look completely similar in enhanced dark field, and even if I go to the spectral imaging, they also look completely similar. They're like a mirror, basically. They just mirror the lamp that I illuminate my samples with. So yeah, they are very similar. Of course, you can, if you have carbon nanotubes, you can differentiate it on the shape. If you are using cells seeded on a glass slide instead of a histological sample, how do you prepare the sample? Is the preparation similar to that of optical microscopy? Yeah, it is optical microscopy. So the stand is actually just a standard bright field stand, microscope stand. So you should just you can take any sample that you have been using in another microscope and take to the dark field. And is it also possible to detect nanoplastics? Yes, I've seen some examples of that. So I think it is possible. And if you go to CITUVIVA's homepage, they have actually a small video on that, on nanoplastics, as I believe. We were struggling to differentiate particles having similar spectral features. Yes, me too. Black particles such as silver, platinum, or carbon nanotubes were quite difficult to differentiate from one another. Have you ever tried to study different particles in the same sample? No. So the studies we do, we only have one particle at a time. At Simon, I haven't done any imaging, but I'm exposing cells simultaneously to 2 nanoparticles. Okay, therefore, was wondering if it was possible to differentiate the 2 in a sample. Yeah, it really depends, because in the Darkfield microscope, you don't have the resolution of EM, of course. So if it's 2 spherical particles and it's not any plasmonic, so they don't have any kind of special optical properties, then they will probably look similar in Darkfield. Have you looked at shifts in the hyperspectral image maxima, as they are supposed to display nanoparticle biomolecule interaction? And how are your experiences regarding this? Yeah. So what I see in our sample, which is mainly tissue samples and also mainly stained with hematoxylin and eosin, is that even within one particle agglomerate, you will have a lot of different maxima, and that these maxima also, you can find the same in these scattering artifacts. So at the moment, in our hands, this hyperspectral imaging is not specific enough. I mean, at least I feel that I can differentiate better based on the appearance and the location in tissues than I can with the spectra. But it's definitely something that is under development, and I think, I think we will be able to push this technique further and further, and hopefully it will become more specific, also for non-plasmonic particles. Yeah, I've tried DQ12. I couldn't find it. It was in lung tissue, and I couldn't see it neither in bright field or enhanced dark field. And honestly, I don't know why, if it's because it forms these microcrystals, and actually nanoparticles give a higher scatter signal usually than micron particles. But I'll try again, so I'm not completely sure about the DQ12. Did you succeed in identifying any unknown particle by comparing spectra from a library? No, I did not. There is one really good publication on using this spectral imaging for identifying particles, but that's plasmonic particles. And it's used, I think it's been used also in, if it's not in tissue, like in, I think it was wastewater and other types of applications. I think you can go a bit further there. For sample preparation, would spheroids embedded in a matrix be possible to analyze using this technique? Yeah, so what we did in patrols was to embed the spheroids in, I think it was agarose maybe, or something where you're able to make thin sections. You need sections of these 5 micron thickness, more or less. It just needs to be transparent to light, and then you can look at the spheroids. So if you can section them, that would be good.
Thanks a lot. So this was quite an extensive Q&A session.
Wonderful. I'm happy.
Wonderful, yes. I'm very happy, actually. So people were still maybe present throughout the entire day and still ready to very critically ask many things regarding this very attractive technique, of course. It's a very cheap instrument, as all of us know. This was very nice. The entire session of advanced cell culture models was very informative, though. And I hope also the morning session was very informative for the community here. I wish to thank again all the presenters from the morning on until the very late afternoon now. And if there are no further questions, I would close the training day for today. Stay tuned with us with the working group A. We are going to, of course, try to cross-communicate advancements in the field from projects to serve the community and also beyond, of course. We will try to make as much as possible available all the things that have been presented today and shared with us will probably pop up in some NanoSafety Cluster newsletters, the links and things like that. We'll also try to use the recordings into a kind of teaching tools, teaching videos, educational material. Thanks a lot for everybody staying that long. It was again an interesting day after a long week of presentations throughout the NanoSafe Digital Conference. Thank you very much, Simon, and your team at CEA for organizing the entire Congress and giving us the opportunity to meet, although virtually, but still to share our results, fascination for the advancement of the field, for new models, for new in silico tools and methods, and what we heard in the morning. Goodbye from my side, from the working group and from the NanoSafety Cluster. Have a nice continuation in your laboratories. Talk to you another time.